Welcome to another Deep Dive, listeners. This time, we're going to try and wrap our heads around planar-rooted line arrangements and how they connect to scattering processes in physics.
Yeah, this is going to be fun.
Yeah, you might be
I'm
thinking,
excited.
how can simple lines on a plane, help us understand the complex way that particles interact?
Yeah, well, it's actually pretty remarkable.
Well,
You can think about these arrangements as these diagrams with lines that represent particle paths, right?
Okay.
And they give us this visual language to really grasp the intricacies of scattering in these 1+1 dimensional systems.
Okay.
It's kind of like a geometric code that unlocks the secrets of how particles behave.
I'm already intrigued.
Yeah.
We're not just looking at these arrangements by themselves, are we?
Oh, absolutely not.
We're going to see how they can be combined in ways that reveal, like, a deeper structure.
Exactly, yeah.
Right.
We're going to get into this world of operads, which are these mathematical structures that give us these rules for combining objects.
Yeah.
And in this case, it'll be our line arrangements.
Okay.
And what's really fascinating here is that we're going to come across not just one, but two distinct operad structures.
Wow.
And these lead to a deeper understanding of something called factorized scattering.
Cool.
Which is this idea that complex interactions can actually be broken down into simpler ones, like a sequence of them.
That's fascinating.
Yeah.
Okay, so we're dealing with purely elastic scattering in a system of classical particles on a line.
Yes.
Can you break down what that actually means?
Sure, yeah.
What does that look like?
So imagine particles with the same mass, right? They're all moving on a line. Their interactions are governed by these repulsive symmetric potentials.
Okay.
Think of it like billiard balls bouncing off each other perfectly. So that's what we mean by purely elastic. No energy's lost during these collisions.
Okay.
And
so it's like a perfectly ideal system.
It is, yeah.
Right.
It is an ideal system.
Okay.
And now, if we think about the distant past and the distant future, these particles are so far apart that they're not actually interacting. We call this asymptotically free. So the real action happens when they come close and collide. Right. That's where the scattering diagrams really capture that action.
Okay, so each line in the diagram is like a particle's path.
Exactly.
And slope is like its momentum.
Exactly. Yeah.
And the intersections are like the collisions.
The intersections are the collisions.
Okay, now hold on a second.
Yeah.
Do these diagrams actually show us, like, the exact curved paths of the particles as they get close to each other?
They don't.
Or is it more like a...
They just show us a straight line.
Asymptotes.
Okay.
So it's like a simplified view.
Yeah, it's a simplified...
Highlighting the key parts of the motion.
It is. It's highlighting the essential aspects.
Okay. And because we're only working with, purely elastic scattering on a line, something really important happens here.
Yes.
What is that?
The order of the particles is preserved.
Okay.
They can't pass through each other.
Oh, I see.
They can only exchange momentum during the collisions.
So that ordering...
It's a fundamental...
constrains how they can interact.
Absolutely.
Okay.
Yeah.
So to analyze all this...
So we've got two main perspectives to look at these dynamics.
Okay.
One is reflection.
Okay.
And one is transmission.
Okay, so reflection focuses on...
how the momenta are exchanged during those collisions.
Like tracking billiard balls after each shot.
Exactly, yeah.
Okay, and what about transmission?
So in transmission, the particles keep their original momenta, but they change their order due to the interactions, and that leads...
So they kind of slide through each other.
Yeah, you can think about it that way.
Okay.
But that sliding results in these shifts in their final positions.
So they don't end up where we'd expect them to if there were no interactions.
Exactly.
Well, I see.
We call these discrepancies phase shifts.
Okay.
And they're denoted by this symbol for the ith particle.
Okay.
And they basically quantify how much the interaction has changed the particle's final position.
Right, compared to its undisturbed path.
Exactly.
Yeah, so the phase shift is like...
Yeah, think of it like a fingerprint of the interaction, right? It reveals how the particles have been influenced by each other.
Oh, okay.
And this is going to be really important later.
Yeah, I bet it connects to that S matrix, right?
You got it.
The one that tells us all the probabilities of the different outcomes.
You're exactly right.
Okay, cool. So
this transmission perspective.
Yeah, it connects to the idea of factorized scattering.
Okay.
We can think of a multi-particle scattering process as a series of two-body interactions, each one contributing its own little phase shift and affecting the order. It's kind of like a chain reaction of these subtle nudges that shape the final outcome.
Interesting.
Yeah.
Okay, so we're seeing these two sides to scattering, right?
Yeah, we are.
We've got reflection, which is all about the momentum exchange, and then transmission, which is focusing on these changes in order and these phase shifts.
That's a good way to put it.
Okay.
Yeah. We've been focusing a lot on these asymptotic lines in the scattering diagrams.
Yeah.
But we haven't really talked about...
Yeah, what about the actual paths of the particles?
Right, near those interaction points.
Yeah.
Right, so...
The diagrams are like a skeleton. Yeah, they are.
Right.
But they don't show us how the particles, curve and swerve.
Right, how the edges...
Like close encounter.
Yeah, exactly.
Yeah.
So the details of those actual paths depend on this thing called the interaction potential, which is a function that basically describes the force between the particles.
I gotcha.
But the scattering diagram, with its focus on those asymptotes, it kind of elegantly abstracts away those finer details while still capturing...
So it's like a simplified representation, but it still gives us a lot of info.
It gives us the essential.
Yeah, That's really neat.
Yeah.
It's kind of counterintuitive that we can get so much information just from those lines.
Yeah.
But it works.
It does.
All right, so we've laid some groundwork with,
purely elastic
scattering.
Yep.
And these two different views of particle dynamics.
Yes.
Now,
I'm ready to try and tackle those operads.
Operads. Okay. They might seem daunting at first.
Yeah.
But once you...
But they're powerful tools.
They are powerful.
Right.
Yeah.
Once you grasp their essence.
Once you get the idea.
They're basically
like sets of rules for combining.
Rules for combining
things in a very structured way.
Right. Consistently.
Yeah. Consistently.
In a consistent way.
It's like...
You can think of it like building with Legos.
Yeah.
Yeah. Where each block...
Yeah, each block has its shape.
Yeah, it's got a specific shape, and you combine them.
And there are rules.
There are rules, yeah.
To create these intricate...
To create, these structures.
Right.
Yeah, and just like Legos come in different shapes and sizes, there's a whole universe of operads, each with their own set of rules and potential application.
Okay, so a key property of operads, the key property
is this
generalized associativity.
Associativity.
Like, that familiar associative property from algebra.
Right.
Like A plus B plus C equals A plus B plus C.
Yeah.
But it's applied to...
What, more complex
combinations. Essentially, it means that the order in which you combine things shouldn't matter. As long as that overall structure stays the same. So
like with the Legos, it doesn't matter if I build the left wing of my spaceship first.
Yeah, it doesn't matter which wing you build first.
Right, or the right wing.
Exactly.
The final structure is the same.
It's the same spaceship.
Okay, cool.
So relating this back to our particle configurations, we can't just lump two configurations together.
Right.
We might
break the order.
We might break the order, right? We might have particles overlapping. Right, yeah.
So the operad gives us this way to insert one configuration into another.
Okay, so instead of just merging them.
Yeah, instead of just merging...
I'm going to do this.
We need a well-defined way to insert one, between specific particles of the other.
Okay, I see. Like adding a new section?
Yeah, like adding a new...
To a train while keeping the order.
Yeah, you got to keep the order.
Okay, but here's the thing.
This is a challenge.
This insertion isn't unique.
It's not unique.
Unless we have some guiding principle.
Unless we have a guiding principle.
And that's where the operad comes in, right?
That's where the operad steps in.
So the operad provides that.
It provides that guiding principle.
Yeah, rule.
The set of rules,
That makes the insertion.
Yeah, it makes it unambiguous.
Unambiguous and keeps everything consistent.
And ensures that structure is preserved.
Okay, this is starting to click.
It is, yeah. So we've got this concept of operads. Right? These sets of rules for combining things. And this really crucial property of generalized associativity.
Generalized associativity. Now, to make this a bit more tangible...
Yeah, let's make it real.
We're going to look at an analogy with tilings.
Okay.
Look where's this going.
These tiling operads, they offer a really helpful visual way to grasp these concepts.
Okay.
So let's think about L-shaped Tromino tilings.
Okay.
Imagine covering a larger L shape.
Okay.
Using smaller L-shaped tiles.
Like those classic tiling puzzles?
Yeah, exactly.
Yeah.
It's amazing how these intricate patterns
it's really cool.
emerge from just arranging these simple shapes.
Yeah.
So in this context, the arity of a tiling is simply the number of tiles it has.
So the arity is like a measure.
It's a measure of complexity.
Yeah.
Tiling with more tiles has a higher arity. Makes sense.
And composition in this context is substituting one tiling into another at a specific tile position.
Okay.
So imagine replacing one L tile in a larger L-shaped tiling with the whole new L-shaped tiling.
Okay.
But scaled down to fit.
It's like zooming into a tile and finding a whole nother level
of detail, right.
A whole other level of detail.
Yeah.
And this composition is governed by the Operads structure. We can represent these tiling operads mathematically using something called tiling words.
Tiling words.
Which are elements of this thing called the word operad.
Okay.
Where G is the group of allowed tile transformations. These tiling words basically encode the sequence of transformations, like scaling, translation, rotation.
Right, so it's like a set of instructions.
Yeah, think of it like a set of instructions.
For creating the tiling. And there are these conditions on these words, matching and normalization conditions, to make sure that they actually represent.
So it's like making sure all the Lego blocks connect properly.
It's a valley.
And the whole structure is aligned.
Yeah, the matching condition makes sure that the tiles fit together at the boundaries.
Gotcha.
And the normalization condition fixes a specific reference frame
I see.
for the whole tiling.
So how does this tiling analogy?
That's a great question.
Yeah.
And that is actually where we'll pick up in the next part.
Okay.
We can think of the points on the line as the boundaries of the tiles.
Okay.
And the spaces between the points are like the tiles themselves.
Oh, okay.
And this sets the stage for building an operad for those static particle configurations, which then paves the way for understanding the dynamic world of scattering.
Okay, great. I'm excited to keep going.
Me too.
This is really interesting stuff.
Yeah, it's cool stuff.
Okay, so we'll pick up with that.
We'll pick up with that in the next part.
Okay, thanks.
That's good.
Okay, my mind is already kind of buzzing with these tiling operads and how they connect to those particle configurations.
Right.
I'm ready to see how we get from these static points on a line to like the actual dynamic world of scattering.
So let's build that bridge.
Okay.
Remember when we talked about that configuration space?
Yeah.
Yukon over 01?
Yeah, that's the space of all the different ways we can arrange those points on the unit interval.
Exactly.
From 0 to 1.
Yep. And what's really cool is this configuration space, it actually has an operad structure naturally.
Wow. Okay. We can insert intervals.
We can insert intervals within intervals.
Right.
So picture a line segment, divided into smaller segments by these points. We can take any of those smaller segments and divide it even further by inserting more points.
Right.
That's our composition operation.
Oh, okay. So it's like a set.
Yeah, you can think of it as
of these nested intervals.
Nested intervals, yeah.
Okay.
Each one containing its own little configuration of points.
Okay, to make this more concrete, can we like visualize each configuration as a point in like a higher dimensional space?
Exactly.
Okay.
The lengths of those smaller intervals, they become our coordinates.
Okay.
So for example, if we have 3 points dividing our unit interval, we get 4 smaller intervals.
Right.
Yeah. Their lengths, we can call them 1, 2, 3, and 4. They become our coordinates. And they have to satisfy this equation. 1 plus 2 plus 3 plus 4 plus 1.
Right, because the total length.
Yeah, because the total length has to equal.
Has to equal 1.
Yeah, the original unit interval.
So we're mapping these.
So we are
mapping them onto
these geometric shapes.
Yeah, these geometric shapes.
In higher dimensions.
In higher dimensions.
Using the lengths as guides.
Use the lengths as guides. Exactly.
That's pretty neat.
And that equation that defines the sum of the lengths that actually defines the geometric object called a simplex. And in this case, with 4 coordinates, it's a 3 simplex, which is a tetrahedron. And any point inside this tetrahedron represents a unique configuration of 3 points dividing that unit interval.
So we're connecting these simple point arrangements.
We are,
to these elegant
to these beautiful
shapes in higher dimensions.
Yeah, it's like a hidden world.
Yeah, a hidden world of structure.
Of structure.
And being revealed.
It is. And this connection to simplexes.
Right. It really highlights the Operads structure.
How so?
Composing two configurations.
Okay.
It's like taking a point in one simplex and mapping it onto a face of a higher dimensional simplex.
I think I'm starting to see this.
Yeah.
Okay, so we've got this really neat Operads structure for point configurations on the unit interval.
On that unit interval.
But we want to describe scattering, which happens
on the whole line.
On the entire line.
Not just a segment.
Not just a segment.
So how do we...
Yeah. How do we make that leap?
How do we make that leap? Right.
Yeah.
That's a crucial step.
Okay.
There's a couple of ways to approach it.
Okay.
One way is to use this thing called a homeomorphism.
Okay.
Which is like a continuous stretching and bending.
Right, okay.
To map that unit interval onto the entire real line.
So we could stretch it out.
Yeah, we could stretch it out to infinity.
To infinity in both directions.
In both directions.
And the Operads structure would still be there.
And the Operads structure would be preserved.
Because it's topological.
Because it's topological.
Okay.
Meaning it's preserved under these continuous transformations.
Okay.
But there's another, maybe more natural way to approach it.
Yeah.
That really leverages the geometry of the line itself.
Okay.
The key insight here is that any finite configuration of points on the real line, it's always contained.
Yeah, we can always find the smallest...
within some finite interval.
Interval that captures all the points.
Exactly. And we can map that interval onto any other interval using an affine transformation.
It's a combination of scaling.
Using a standardized measuring stick.
Yeah.
We scale things down.
Yeah, scaling, translating.
To our ruler, make our measurement.
Or possibly reflecting.
Right. And then scale everything back up.
That's a great way to put it.
So to formalize this, we use this thing called Proposition 1 from the paper, which gives us a way to extend an Operads structure from a normalized setting to a more general one.
Okay.
So in our case, our normalized setting is UConn 0, 0, 1.
Right, that's the unit interval.
And our general setting is UConn, the space of all finite point configurations.
Right, on the entire line.
On the whole real line.
Okay, so Proposition 1?
So Proposition 1 is like a bridge between these two worlds, allowing us to use that Operads structure we have for UConn 0, 1, to build one.
To build one for UConn.
For UConn, exactly. Okay, so to use Proposition 1, we've got to define this.
We need to define
normalization map.
Right, normalization map.
What does that look like? So this map takes any point configuration on the real line and finds this unique affine transformation that scales and translates it. To fit within that unit interval, we can represent these affine transformations using matrices.
So each configuration gets its own matrix.
Exactly.
That normalizes it.
That normalizes it.
Okay.
And Proposition 1 tells us that if we can define this normalization map in a way that's compatible with the Operads structure on UConn 0, 1, then we can lift that structure.
So UConn too.
UConn friend, exactly.
Okay, but how do we
so how do we
make sure that normalization map...
How do we make sure that it's compatible? That's where the details of the proof of Proposition 1 come in. The key is showing that the composition of normalized configurations followed by normalization is the same as normalizing first and then composing.
So it doesn't matter?
It's like saying the order...
What order we do it in?
Yeah, the order in which we normalize and compose doesn't affect the final result, which is really important.
Right, to keep the Operads structure.
We're preserving that Operads structure.
Okay, so it's all about consistency.
It's all about consistency.
Yeah, compatibility.
Yeah, compatibility between those operations.
It sounds like there's some pretty complex math in there.
There's some intricate mathematical arguments involved. The proof involves carefully constructing that map and demonstrating its properties. For instance, we need to make sure that it handles the insertion of one configuration into another correctly. And we also need to show that it respects associativity.
Right, of course.
Which is a fundamental property of Operads.
Right, okay. It's amazing how these, like, abstract mathematical concepts can help us understand something like, you know, the scattering of particles.
It's a testament to the power of math. to reveal those connections of patterns in the natural world. So this operad on ucompar, which we'll call ESC, that's our stepping stone to understanding the operad of scattering diagrams. It captures that essence of combining those static particle configurations. And we'll use that knowledge to delve into that dynamic world of scattering.
This is really exciting. I'm ready to see how it leads us to the operad of those scattering diagrams.
Let's move on to that. Remember those planar-rooted line arrangements?
Yes.
Those are the elements of L, and they encode the scattering processes beautifully.
With that root line representing the initial time and all the other lines.
All the other lines?
With different slopes.
With different slopes.
Representing the momentum.
Representing
the particles, right. Exactly.
Okay. And remember those ordering conditions?
Yes, those ordering conditions. No parallel lines.
No parallel lines.
Intersections only in the upper half plane.
Upper half plane,
And the order of those intersections on the root line. We're explaining the particle order.
Exactly. Those are crucial.
Those are really important.
To make sure our arrangements really represent the physics of purely elastic scattering.
It's like a set of grammatical rules.
It's like a set of rules.
Making sure our diagrams make sense.
Making sure it makes sense. Now, to understand how these arrangements combine, we need to look at the operad structure of L. We use this symbol to represent the composition. Let's unpack how it works geometrically.
I'm all ears.
So
this is where the magic happens.
This is where the magic happens. Let's say we have two arrangements, P and Q.
P and Q.
To compose them, we write P, SQ.
P, A, Q.
We first need to identify 3 specific points on P. These points are the intersection of the root line with the ith line. We'll call that pi. The intersection of the ith and I plus 1th lines, which we'll call pi plus 1.
Pi I plus 1.
And finally, the intersection of the root line with the I plus 1th line, which is pi plus 1.
Pi plus 1.
So we're basically selecting these 3 points.
Like we're marking the spot.
We're marking the spot.
Where the composition is going to happen.
Where the composition is going to happen. Now we do the same for Q. Identifying 3 points. Q1, Q1 meter plus 1, and QM plus 1.
QM plus 1.
Where M is the number of lines in Q.
So we're doing the same thing.
We're the same thing.
Picking our 3 points.
Picking 3 points. Now here's the key insight. There's this unique affine transformation that maps the triangle defined by Q1, Q1 meter plus 1, and QM plus 1 onto the triangle defined by pi, pi plus 1, and pi plus 1.
So we're stretching and squeezing Q.
We're stretching or squeezing.
To fit it into P.
Sliding to fit perfectly into that region on P. And this affine transformation lets us combine those arrangements. We apply this transformation to Q. And the resulting arrangement, PAQ, is simply the union of the lines in P and the transformed lines of Q.
So we're not just like overlaying them.
No, we're not just overlaying.
We're really weaving Q into P.
We're weaving it in using this transformation.
It's like a dance.
It's a beautiful dance.
Of lines and spaces.
Of lines and spaces. I love that.
And it's this...
And it's this precise integration that makes L a true operad. Remember Theorem 1?
Good job.
It states that L, with this composition, satisfies those generalized associativity conditions we talked about earlier.
So we can combine arrangements.
It means we can combine multiple arrangements
in different ways.
And
get the same result.
And still arrive at the same final result. It doesn't matter how we group them.
Theorem 1 is like our seal of approval.
It's like a seal of approval.
That this structure...
It's built on solid mathematical ground. Now, the proof of Theorem 1, as you might imagine, involves some pretty intricate arguments. But the essence is to show that this composition really respects those operad axioms.
The operad axioms. And a key strategy here.
A key strategy is to focus on
normalized arrangements, right?
Yeah, these normalized arrangements.
Remind me what those are again.
Of course. So normalized arrangements are arrangements in L where we have these additional constraints on the positions of certain lines. Specifically, we require the root line to be the line T0, the first line to be Q plus T0, and the last line to be Q plus T1.
Q plus T1. Okay.
So it's like setting up.
So it's like a standardized coordinate system.
Yeah, it's like a standardized coordinate system.
For our arrangement.
For our arrangements.
Yep.
And any arrangement in L can be transformed into a normalized arrangement using a no-finite transformation.
We're shifting.
Yeah, it's like shifting, scaling, rotating.
It's that measuring stick idea again.
It is. It's that measuring stick idea. We're normalizing to simplify the calculations and then transform back to the original system. And working with these normalized arrangements makes the proof a bit more manageable. We can represent each normalized arrangement using a tuple of matrices. Where each matrix encodes the position of one of the lines.
So we're translating the geometry of the lines into matrices.
Into the language of matrices. Right. And using that matrix representation, we can show that the composition operation, when applied to these normalized arrangements, satisfies the Operad axioms. And then using proposition 1, we can lift the structure
to the full
Operad L, showing it's a true Operad, even without those normalization constraints.
So we prove it for a simpler case.
We prove it for the simpler case.
And then use proposition 1.
And then use proposition 1
to generalize.
To generalize it. It's a powerful strategy.
Break it down into pieces.
For tackling these complex problems, by breaking them down to more manageable pieces.
This really highlights
the
elegance of mathematical reasoning.
It really does. We prove a result in a constrained setting and then use the tools to extend it to a broader class of objects. Now, there's another exciting aspect of L. It has a remarkably simple set of generators.
Generators. What does that mean?
So that means that every arrangement in L, no matter how complex, can be built from a small set of basic building blocks using our composition operation. Lemma 4 from the paper tells us that L is generated by the group of transformations G, which represents all the possible ways to shift, scale, and rotate our arrangements and 3 specific families of binary operations.
So G is like our toolkit.
G is like our toolkit for manipulating
those arrangements.
And these binary operations. And the binary operations are like our building blocks. Exactly. Now, each of those 3 families corresponds to one of the 3 possible combinatorial types of a rank 3 arrangements. So that's the ways to arrange 3 lines so that intersect in the upper half plane. So we have 3 lines intersecting at a point, 2 lines intersecting, and the 3rd one cutting through, or all 3 intersecting pairwise.
So it's like a set of fundamental moves.
Fundamental moves,
that we can use to build. Any scattering process. This is amazing.
It is pretty cool.
We've explored the structure of L. But what about its meaning? Like, how does this connect?
So how does it connect?
To the physics.
Yeah.
That's a great question.
And that's where we'll continue our deep dive in the next part.
I'm excited.
The symmetries of L, they're directly related to physical concepts. For instance, invariance under translations along the coaxis. That reflects that the physics of scattering shouldn't depend on.
Shouldn't matter where it's happening.
Our chosen origin.
Like if it's happening in a lab.
Like if it's happening in a lab.
Or a distant
galaxy.
The interaction's the same.
It's the same. The underlying interaction and the piece symmetry, which involves flipping the diagram about the t-axis, corresponds to time reversal. So it's like...
If we could run the film backwards?
Run the film backwards. It would still be valid.
It would still make sense.
It would still make sense. Like those elastic collisions we
Yeah.
talked about. Watching a video of billiard balls colliding in reverse would look just as realistic.
Exactly.
Okay, cool.
Now, the T-symmetry is a bit more subtle. It involves extending our definition of L to allow for intersections below the root line. And then flipping the diagram vertically.
So we're imagining particles.
You could think of it that way.
Scattering backwards in time.
Yeah, scattering backwards in time.
Okay.
And while this T-symmetry might not have a direct physical interpretation in our classical setting, it actually plays a big role in quantum field theory, where particles can be created and annihilated.
Right.
It's cool to see how these mathematical symmetries kind of mirror and sometimes even foreshadow concepts in physics.
It really shows that connection between math and the natural world.
Yeah.
Okay, now you mentioned another symmetry.
Right.
The Z-symmetry.
The Z-symmetry.
Right. That's really crucial.
That's a crucial
for factorized scattering.
Yes. The Z-symmetry involves shifting those lines parallel to themselves without changing the order of the momenta.
Right. Okay.
Remember how we could use this symmetry to transform any arrangement into one where all the lines intersect at a single point?
It's like collapsing
the collision. Yeah, collapsing all those collisions
down to a single point.
Down to a single point.
Okay.
In space-time.
Yeah.
And this is really...
This is like the heart.
This is intimately connected to the idea that we can decompose multi-particle scattering into a sequence of two-body interactions.
Okay.
We can think of those parallel shifts as representing those individual two-body collisions.
Right, like each contributing.
Yeah. Each one contributing
to the overall process.
To the overall scattering process.
Yeah.
So the Z-symmetry.
It's like the math version of factorization.
It's like the mathematical embodiment of factorization.
Right.
It lets us break down those complex interactions.
Into those simpler pieces. Okay, and this insight
enables us
to formalize the connection between and scattering theory. Using Operad morphism. These morphisms are maps between operads that preserve...
Right, they're like the translators.
Yeah, think of them as translators between these two languages.
Right.
They make sure the rules of the operads are respected.
Right, the grammar's got to match up.
The grammar's got to match up, exactly. Now, definition 3 from the paper formally defines a scattering theory as an operad morphism, which we'll call S from our operad, L
to another operad, which we'll call P. This operad, P, represents the physical quantities.
Like the S matrix.
Yeah, like the S matrix elements.
Right.
Exactly.
That tells us the probabilities.
That tells us the probabilities of different outcomes.
Yeah. Okay.
So we're mapping those arrangements.
Right, those abstract line arrangements.
In L. Yeah, in L.
Onto concrete physical data.
Yeah, like those S matrix elements.
Like those S matrix elements in P.
Physicists use.
Yeah, that physicists use to make predictions about experiments.
Okay, cool.
Now, what's really amazing here is this operad morphism.
Right.
It has to respect the operad structure.
Right. So the way we combine things in L has to be consistent with how we combine
it has to be consistent.
The physical quantities in P.
Yes,
exactly. It's like making sure the grammar's
got to match up.
Matches up between the two languages.
Yeah. So our translation makes sense.
Right. Okay. And this requirement to preserve the structure it leads to a profound insight. It turns out that the Yang-Baxter property of a scattering theory, this fundamental property that ensures consistency and factorizability, it can be expressed in terms of this operad morphism S and the Z-symmetry map P.
Wait, so you're telling me the Yang-Baxter property, which is usually like this really complex equation.
It's a complex equation with matrices and indices.
Yeah, it can be captured.
It can be captured.
Just using operads and the Z-symmetry?
Using the language of operads and the Z-symmetry.
Wow, okay.
Yeah, the Yang-Baxter equation.
Okay.
It basically says that if we have 3 particles scattering, it doesn't matter if we first let particles 1 and 2 interact, then 2 and 3, and finally 1 and 3.
Right.
Or if we switch up the order.
Yeah, mix it up.
The final outcome should be the same.
It should be the same.
And this property is directly reflected in the structure of L.
Okay.
And the existence of this Z symmetry.
So this abstract mathematical structure, L.
Exactly.
It's not just a convenient way.
It's not just a convenient way
Very
to visualize things.
To visualize things.
It's actually encoding this deep principle of factorizability.
That deep physical principle.
That's amazing.
Yeah, it highlights...
It shows how math isn't just...
how math is
Still for calculation.
It's not just a tool for calculation.
Right.
It's a language.
It's like a language
for expressing truths.
For expressing truth.
About the universe.
Okay, so we've got this operad morphism S.
We do.
That maps our arrangements in L onto the physical data in P.
Onto that physical data.
And we've seen how that Yang-Baxter property is connected to the morphism.
Connected to the morphism.
And that Z symmetry and the Z symmetry.
What are the implications?
So what are the implications of all of this?
Yeah, what new insights do we get?
What new insights do we gain from this perspective? Yeah. Well, first, it gives us a much deeper understanding of factorized scattering.
Okay.
We're not just relying on algebraic manipulation.
And we're seeing how it emerges.
We're seeing how it emerges.
From the geometry and the combinatorics.
It's like we've gone from a sketch.
Exactly.
To a full 3D model.
To a full 3D model.
Okay, cool.
And second, this framework gives us tools for studying and classifying different scattering theories. By looking at the properties of different operad morphisms, we can get insights
into a different system,
into the behavior of different physical systems.
It's like we have a master key.
It's like a master key.
That unlocks all these different theories.
It unlocks a whole world of scattering theories.
We can compare and contrast them, understand their structure and their connection to those physical principles.
Okay, cool.
And third, and maybe most importantly, this opens up new avenues for research.
Okay, like what?
So we can ask, how do we extend this?
Right, because we've been working...
This operatic perspective.
1 + 1 dimensions.
Higher dimensions.
Right, but the real world.
The real world has more than one spatial dimension.
Right, right, okay.
Can we construct operads that capture scattering in 2 + 1?
Okay.
Or even 3 + 1?
Right.
Can we find
analogs of the Z symmetry?
Analogs of the Z symmetry.
And the Yang-Baxter.
And the Yang-Baxter property.
In these higher dimensional settings.
Exactly.
It feels like there's so much.
Like we're standing
at the edge of this vast uncharted territory.
It's exciting.
It is exhilarating.
Okay.
And this is just the tip of the iceberg.
Wow.
We can also ask how this operatic framework might help us understand scattering in more complex systems. Systems with internal degrees of freedom. Systems with particle creation and annihilation.
Right.
Systems governed by quantum field theory.
Yeah.
The possibilities.
The possibilities seem endless.
Yeah, endless.
This has been an incredible journey.
It has.
We started with simple lines.
Simple lines on a plane.
On a plane.
And we've ended up with a whole new perspective.
Yeah. A whole new perspective on scattering.
On the nature of scattering.
Its connection to these fundamental principles.
Its connection to those fundamental principles.
And all this new research that can be done.
And a whole new landscape of research.
Yeah.
It's a testament to the power of math.
It really is.
To illuminate the hidden depths of the physical world.
I feel like we've only just scratched the surface.
We've only just scratched the surface.
But I'm walking away with a new appreciation for operads.
For operads. They're not just abstract toys.
They're not just abstract toys.
They're really keys.
They're keys.
To understanding the universe.
To understanding the universe.
Thank you so much for taking us.
It's been my pleasure.
On this deep dive.
It's been fun.
This is really, really cool stuff.
It is cool stuff.
I know our listeners are going to be thinking about this.
I hope so.
For a long time.
Me too.
So thanks again.
You're welcome.
Welcome to another deep dive, and this time we're going to be exploring scattering diagrams and operads. Specifically, we're taking a look at this paper called Scattering Diagrams and the Operad. It's going to be a fun one.
Yeah. This is a really cool area where geometry and algebra, they kind of come together.
Oh, yeah.
So scattering diagrams, you know, they're these visual representations of how particles are interacting. You can actually see the dynamics playing out. And then the operads provide, you know, the mathematical framework for really understanding the structure underneath it all.
Yeah, I like how this source starts out with these visuals. You know, they go right into these scattering diagrams.
Yeah.
And they distinguish between two ways of kind of picturing them. Reflection and transmission. So it's like having these two different lenses to look at the same thing.
Yeah, exactly. And, the paper uses this figure, too, to illustrate these two perspectives. So in this reflection picture, you have these lines that are actually representing the particles' trajectories.
Oh, cool.
And then when they collide, those lines deviate, which reflects how the particles change direction when they interact.
Yeah, I can see how that would be a very helpful way to visualize, the actual paths of the particles.
Yeah, it's very intuitive, right?
But then you've got this transmission picture, which the source describes as kind of a different approach, where the lines remain straight.
Yeah.
They don't bend, and they represent these asymptotically free zones where the particles aren't interacting. So instead of bending, the lines might jump over each other.
Right.
Which indicates like a reordering of the particles after the collision.
Yeah, precisely. So in this transmission picture, it's not about the specific trajectories. It's more about how the particles rearrange themselves after the collision.
Right.
So you can imagine these straight lines as like lanes on a highway.
Oh, okay.
The particles just zoom along those lanes without actually bumping into each other.
Right.
And this picture lets us introduce this concept of phase shifts, which essentially capture the discrepancies, right, in the particles' positions after the collision. So you compare that to where they would have been if they had continued along their original paths.
So it's like the collision causes this phantom shift in their position, even though their paths remain straight in this picture.
Exactly. Exactly. And these phase shifts, they contain really crucial information about the scattering process, and they're actually directly related to this scattering matrix, also known as the S matrix, which essentially captures the overall effect of the interactions.
Okay. So you're mapping the initial state to the final state.
Exactly.
Okay. So I'm starting to see how these two pictures provide these different perspectives on the scattering event. The reflection one gives us the detailed trajectory, and the transmission one highlights the reordering and introduces these phase shifts.
Yeah.
But where do these operads come into this picture?
Okay.
How do they help us kind of grasp these scattering diagrams in a more, deeper way?
So that's where, the paper really starts unpacking this power of operads, and they provide this framework for understanding how to combine and manipulate these scattering diagrams, mathematically rigorously.
Right, yeah.
So you can imagine you've got two separate scattering diagrams, and they represent two initial configurations of particles.
Okay.
And the paper, it highlights this challenge of combining them in Figure 3.
Yeah, I noticed that you can't just smush them together haphazardly. You've got to make sure that the order is preserved.
Right.
You don't have any overlaps. It's almost like fitting together puzzle pieces, but you've got to respect the structure.
Exactly. And that's exactly what this composition operation,
Okay.
from operad theory allows us to do.
Oh, interesting.
It gives us this very precise way of inserting one configuration into another.
Okay.
So you can think of it as nesting,
Right.
nesting these scattering scenarios within each other.
Okay, so it's not just combining the pictures, it's establishing a mathematical rule for how to do that in a way that makes sense physically.
Yeah, precisely. And the paper emphasizes this crucial aspect of this composition, which is that it has to obey this kind of chronological symmetry.
Oh, interesting.
So the order in which you compose multiple configurations, it shouldn't actually matter.
Oh, okay.
As long as that relative order of insertions is maintained.
Right, so if I've got configuration A, B, and C, and I stick B into A and then C into the result of that, that should be the same as me sticking C into B first and then sticking that whole thing into A.
Right, precisely. As long as, B ends up inside A and C ends up inside B,
right,
the final result should be identical, and this property is actually known as associativity in mathematics.
Okay.
And it's a really fundamental requirement for operads.
Okay.
It ensures that this way we're combining these scattering diagrams is consistent, and it doesn't depend on any arbitrary choices.
Yeah, that makes a lot of sense. I did notice that the source even provides this visual representation for this nested composition.
Yeah.
Using rooted trees in Figure 4, with each branch of the tree representing a configuration being inserted into another.
Exactly. It's like this family tree for scattering diagrams.
That's a great way to put it.
Yeah.
And this whole idea of composing the scattering diagrams It's really fascinating that it has this really solid mathematical foundation.
Yeah.
And I know that Theorem 1 in the source, that's where it really comes in.
Yeah, exactly. So this Theorem 1 basically states that there is a way to consistently define this Operad structure on the space of all scattering diagrams.
So it's not just us making this up, it's actually a real mathematical thing.
Exactly, exactly. So the theorem actually assures us that we can work with these compositions in a well-defined way.
Right.
And it opens up the door to exploring all these deeper implications of this Operad structure.
And this is where the source introduces Morse. This operad is specifically designed for scattering diagrams. But I'm curious, how do we actually construct this Morse operad?
So the key idea is to use these things called affine transformations, geometric operations that preserve lines and parallelism.
Right, like translations and rotations, things like that.
Exactly. So you can think of these transformations as allowing us to glue different scattering configurations together while still respecting their geometric structure. And, figure 15 in the source actually illustrates this gluing process really well.
Yeah, so we're using these transformations to carefully stitch these diagrams together and making sure everything lines up and that those relationships are preserved during the composition process.
Exactly. Exactly. And, this Norse operad, like any other operad, it has these things called generators, building blocks.
Well, yeah.
And these generators represent, the most basic types of scattering events you can imagine. So, 2 or 3 particles interacting.
Gotcha.
And figure 16 in the source, actually, it beautifully shows these generators.
So by understanding those basic interactions, we can then use the Operads rules to essentially build up any complex scattering diagram we want.
Exactly. So it's like the system, right?
Okay.
For decomposing complicated scenarios into these fundamental building blocks. And it reveals all this underlying structure and relationships that might not be obvious when you just look at it.
This is incredibly powerful. It's like uncovering this hidden language for describing particle interactions.
Yeah.
Where you break these complex events into simpler components that are governed by these operatic rules.
Yeah. And what's amazing is that this language is not just descriptive.
Right.
It actually helps us predict things.
Oh, wow.
By understanding the structure, we can start to predict how more complex systems will behave.
Okay.
Just based on the properties of those fundamental interactions.
This is getting me really excited. We're starting to see these deep connections between these abstract math concepts like operads and the real-world physics of these interactions. But before we go too crazy, let's maybe take a closer look at some specifics about this operad and how it actually helps us understand the symmetries involved in these scattering processes.
Yeah, that's a great point. The operad structure really lets us dive into these symmetries, which gives us all these insights into the physics. So the source, it introduces this concept called z-symmetry, which involves shifting these lines in a scattering diagram without actually changing their order or the points where they intersect.
Okay, so even though the picture might look a little different after the z transformation, the actual physics of the scattering event stays the same.
Exactly, yeah. And this z-symmetry, it actually hints at something really profound, which is this possibility of factorizing scattering events in certain cases. So we might be able to break down these multi-particle collisions into a sequence of simpler 2-particle interactions.
Wait, so a complex collision is potentially just a bunch of simpler ones happening in a specific order?
That's the idea.
Okay.
Yeah, and this factorization property is actually closely tied to this Yang-Baxter property, which is a hallmark of what we call integrable systems.
Okay.
Systems where we can find exact solutions even when the interactions are quite complicated.
Wow, that's incredible. So this operad structure not only reveals the hidden symmetries, but also points to this possibility of simplifying these complex interactions.
Yeah, exactly.
I'm really eager to kind of dive deeper into these connections and see where they lead us.
Yeah, me too. Me too. The paper also mentions some cool links to other mathematical concepts like polytopes and configuration spaces, which offer even more perspectives on these scattering processes.
It's amazing how this topic just weaves together all these different areas of mathematics. This has already been a fascinating dive. I can't wait to continue exploring these connections.
Yeah, absolutely. It's fascinating how these abstract mathematical concepts, like operads and z-symmetry, can have such deep implications for how we understand the physical world. The paper, it goes even deeper into this connection, highlighting this relationship between the Yang-Baxter property and this operad.
Yeah, I remember that the Yang-Baxter property was mentioned in the source, but I'm not going to lie, some of those mathematical details were a bit dense for me.
Sure.
Could we maybe unpack that a little bit more?
Yeah, absolutely.
What exactly does this property, entail?
Okay, so the Yang-Baxter equation at its heart basically states that in certain scattering processes, those involving three particles, the final outcome doesn't actually depend on the order in which those particles interact. So let's imagine we have particles A, B, and C, right? The Yang-Baxter property basically implies that whether A interacts with B first and then C, or if A interacts with C first and then B, the final state of the system, it's going to be the same.
So it's kind of another manifestation of that chronological symmetry we were talking about earlier.
Yeah.
This idea that the order of operations doesn't always matter.
Precisely. And the remarkable thing is that this seemingly simple property,
Yeah.
it has such profound implications. It suggests that there's this hidden structure within these systems, like a kind of order that allows us to break down these complex interactions into these simpler building blocks. It's almost like having this master key.
Okay.
That just unlocks the complexity of this multi-particle scattering.
I'm starting to get the significance of this Yang-Baxter property now. But how does this relate to the Operad structure we've been discussing? How does Gouldio fit into this picture?
Okay, so that's where things get really elegant. So the source explains that a scattering theory, which essentially assigns these mathematical values to these scattering diagrams, is said to possess this Yang-Baxter property if it factorizes through a specific operad morphism.
A morphism? Could you remind me what that means in this context?
Yeah, sure. So in this case, a morphism is basically a mapping between two operads that preserves the rules of composition.
Okay.
So it's kind of like a translator.
Okay.
That lets us move between these different operad structures while still maintaining all the essential relationships.
So this morphism is kind of like a bridge between two different ways of describing the scattering.
Precisely. And the source focuses on a very specific morphism.
Okay.
It's denoted as AP, that connects our operad, the one we've been talking about, for these scattering diagrams,
Right.
to another operad called Hozasub. And this Hozasub operad, it really captures the essence of this Z-symmetry.
Right, that Z-symmetry, the transformation where we can shift the lines without changing the physics.
Right.
Is a subasub the operad for scattering diagrams where all the lines just intersect at a single point, A?
Exactly.
Okay.
And the fact that a scattering theory factorizes through this morphism P, it means that it's essentially invariant under this Z-symmetry. The math itself might seem abstract, but the key takeaway here is that for these special scattering theories, those that possess this Yang-Baxter property,
Okay.
multi-particle scattering events, they can actually be completely understood just in terms of two-particle interactions.
So we can break down the complexity of this multi-particle collision into this series of simpler two-particle interactions.
Yeah.
All thanks to this factorization.
Yeah.
Enabled by the Yang-Baxter property and, of course, captured by the Operad structure.
Exactly. It's like understanding a complex chain reaction, like with dominoes, by analyzing the interaction between just individual dominoes.
Okay, yeah.
So the overall pattern, it just emerges from those simple local interactions.
That's a pretty remarkable concept. But I'm wondering, does this have any practical applications? Does this extend beyond just theoretical physics?
Absolutely. The source actually briefly mentions this connection between scattering diagrams and polytopes,
Okay.
which are these geometric objects with flat sides.
Okay, yeah.
Specifically, it discusses permutahedra, which are these polytopes whose vertices correspond to permutations.
Permutations, like different orderings of things.
Exactly. So imagine you have three objects, and they're labeled 1, 2, and 3.
Yep.
There are 6 possible ways to arrange them, right? 123, 132, 213, and so on. Each of these orderings, it's a permutation. And if you connect these permutations in a very specific way, you actually get this permutahedron, which is this really beautiful geometric shape.
Okay, I'm picturing this three-dimensional shape with the permutations at its corners.
Right.
But how do these permutahedra relate to the scattering diagrams?
Okay, so the source explains that each scattering diagram can be associated with a specific path within a permutahedron.
Okay.
So as particles collide and their order changes, we essentially move along this path, tracing out the different permutations of their positions.
So it's almost like a map of the scattering process, kind of guiding us through the various possible rearrangements.
Precisely. And this connection to polytopes is really significant because it opens up these new ways to analyze these processes. Polytopes, they have this rich mathematical structure.
Right.
And by connecting them to scattering diagrams, we can start using tools from geometry and combinatorics to gain deeper insights into those interactions. It's like adding another layer of mathematical elegance to this already fascinating subject.
Yeah, it's incredible how this topic keeps revealing these deeper connections between these seemingly disparate areas of math.
Yeah.
And speaking of connections, the source also mentioned something called the Swiss cheese operad.
Oh, yeah.
Can we dive into that a little?
Absolutely. It's this really intriguing mathematical structure with, I think, a surprisingly accurate name.
Okay.
Imagine you take this flat disk, right?
Okay.
And you start cutting out smaller disks from it, leaving behind this pattern that, well, it resembles Swiss cheese.
I can picture that, a disc just riddled with holes.
Yeah. Yeah.
Okay, how does cheese relate to scattering diagrams?
Okay, so the source explains that you can transform each scattering diagram into this Swiss cheese-like shape.
Okay.
By thickening its lines and focusing on a specific region called the upper envelope. And this transformation allows us to study scattering processes using tools from topology, which deals with shapes and their properties.
So we're going from lines and points to shapes and surfaces.
Right.
This topic never ceases to amaze me with its ability to just weave together all these branches of mathematics.
It's pretty cool.
What's the main takeaway here?
Okay.
Why are these connections to polytopes and Swiss cheese so significant?
They really highlight the power of abstraction and generalization in math. So by finding these connections, we uncover these hidden patterns and relationships that might not be obvious at first glance. And it lets us view these scattering processes not as these isolated events, but as a part of this larger mathematical framework. It's like realizing that the same basic principles govern how planets orbit and how water flows in a river.
Right, yeah.
There's this kind of unity underneath this surface diversity.
That's a beautiful analogy.
Yeah.
And this realization, as the source kind of suggests, opens up all these new avenues for research, new ways of asking questions and seeking answers. It reminds us that, the pursuit of knowledge, it's this interconnected journey.
Yeah.
And these unexpected connections can lead to profound insights.
Absolutely. It's like we're exploring this vast interconnected landscape of ideas, and each new connection kind of illuminates the terrain in these unexpected ways. And I think as we continue this exploration, we're likely to encounter even more aha moments, those flashes of insight that connect those seemingly unrelated concepts.
Yeah.
And they really deepen our understanding of this mathematical universe.
This journey into the world of scattering diagrams and operads has already been so insightful. It's revealed this depth and elegance that I really wasn't anticipating.
Yeah.
And the source even hints at these even more exciting possibilities.
Right.
Inviting us to consider how this framework might extend to even more complex scenarios.
Yeah, definitely.
I'm particularly intrigued by this idea of incorporating those particles with those internal degrees of freedom.
Yeah, that's a really fascinating area. So far, we've been talking about purely elastic scattering, right?
Right.
Where particles only exchange momentum or rearrange their order. But in the real world, particles carry all this additional information.
Okay.
Like spin or charge. And those properties can change during interactions.
It's like our billiard balls suddenly have different colors or textures.
Yeah.
And those properties are now affecting how they bounce off each other.
Precisely.
Yeah.
So incorporating these internal degrees of freedom into the Operad framework, it would allow us to study a much wider range of processes, including those relevant to like quantum field theory and particle physics.
It's like opening up this whole new dimension to our understanding of particle interactions.
Exactly. And the real challenge lies in how to represent these degrees of freedom within this Operad structure. So how do we encode those additional properties into these diagrams and the composition rules? That's where the real math innovation will come in.
It sounds like a fertile ground for, future research, really pushing the boundaries of both math and physics.
Yeah, absolutely.
And the source also mentions exploring scattering in higher dimensions, which seems equally daunting to me.
Yeah, it's a big one, We've been working with these diagrams in this two-dimensional plane, representing one spatial dimension and one time dimension. But of course, the real world has 3 spatial dimensions.
Right.
And extending this framework to these higher dimensions, it poses these significant challenges, both conceptually and mathematically.
Yeah, just visualizing these diagrams in 3 spatial dimensions is already making my head spin. It's like trying to juggle 4 dimensions in your mind at once.
Yeah, It's a challenge, but, it's ultimately rewarding
Yeah.
because the geometry just becomes much richer in these higher dimensions. And the Operad structure, it would have to be adapted to handle these more complex configurations.
Right. But the potential rewards are immense. It could give us these new insights into how particles behave in our three-dimensional world.
Yeah,
Perhaps even shedding some light on, some fundamental questions about space and time.
absolutely. And the source. It also encourages us to explore these connections to other areas like configuration spaces,
Right.
which deal with the arrangements of points in space.
Right.
And these things called braid groups, which capture the ways that you can intertwine strands.
It's like we've opened this door to this vast landscape of mathematical ideas with this Operad framework as our guide.
Yeah.
And as we venture further, I'm sure we're going to continue to find those, moments.
Absolutely.
Those flashes of insight that connect those seemingly unrelated concepts.
Yeah, and those moments, they're what make this pursuit of knowledge so rewarding.
Yeah, absolutely.
The beauty of mathematics is in its ability to surprise us, to reveal these hidden patterns and unexpected symmetries.
Right.
And as we've seen in this dive, the Operad approach provides this really powerful lens through which we can view this intricate dance of particle interactions.
It's been a privilege to explore this fascinating topic with you. The source material has really provided such a rich and stimulating foundation for this discussion, and it's left me with a profound appreciation for the elegance and power of mathematical thinking.
Yeah, I agree. It's been a really enlightening dive.
Yeah.
It showcases the remarkable ability of math to illuminate the world around us,
Yeah,
from the simplest interactions to the most complex structures in the universe.
absolutely. And to our listeners out there, we encourage you to continue exploring this fascinating topic. Pick up a book, dive into a research paper, or just let your curiosity guide you. Who knows what amazing discoveries await?
Remember, even the most complex phenomena, they often have these elegant mathematical underpinnings.
Right.
And this pursuit of understanding those underpinnings, it's such a rewarding journey full of, unexpected twists and turns.
So keep your minds open, embrace the power of abstraction, and let the beauty of mathematics inspire you. Wow, this deep dive into scattering diagrams and operads has really been an eye-opener. So many unexpected connections and just this level of mathematical elegance I hadn't really appreciated before.
It is pretty remarkable, right, how these abstract structures, they come from pure math, can provide these deep insights into the physical world,
Yeah.
particle interactions, and the whole thing. And like the paper suggests, we've only just started to scratch the surface of what this operatic framework can do.
Right. The source does hint at some exciting directions for future exploration, particularly extending this framework to handle more complex scenarios. I'm really intrigued by this idea of incorporating particles with those internal degrees of freedom, like you were talking about before.
Yeah, that's a fascinating area. So far, we've been focusing on this purely elastic scattering, right, where particles just exchange momentum or they rearrange their order. But in the real world, particles, they carry all this additional information, like spin or charge.
Yeah. It's like those billiard balls we were imagining before suddenly have different colors or textures.
Right. Yeah.
And those properties now affect how they bounce off each other.
Exactly. So if we could incorporate these internal degrees of freedom into the Operad framework, it would let us study a much broader class of scattering processes, including those that are relevant to quantum field theory.
Right.
And even particle physics.
It's like opening up this whole new dimension.
Yeah.
To our understanding of these interactions.
Exactly. And the challenge here is, how do you represent these degrees of freedom within this Operad structure? Or how do we encode those properties into the scattering diagrams, the compositions, the rules? That's where the real, mathematical innovation is going to be needed.
It sounds like such fertile ground for future research, really pushing the boundaries of, math and physics.
Yeah.
And the source also mentions exploring scattering in higher dimensions.
Yeah.
Which also seems pretty daunting.
Yeah, that's a big one. We've been working with these diagrams in a two-dimensional plane, representing one spatial dimension and one time dimension. But obviously the real world has three spatial dimensions.
Yeah.
And extending this framework to those higher dimensions poses significant challenges, conceptually and mathematically.
Just trying to visualize these diagrams in three spatial dimensions already makes my head spin.
It's a lot to wrap your head around, right?
It's like juggling 4 dimensions in your mind.
It's tough, but it's definitely rewarding. The geometry becomes so much richer in those higher dimensions.
Right.
And the Operad structure have to adapt to handle these more complex configurations.
But the potential rewards are immense. It could give us such new insights into how particles behave in our actual world. Maybe even shedding light on some fundamental questions about space and time.
Absolutely. And the source, it encourages us to explore those connections to other areas of mathematics, like configuration spaces.
Okay.
Dealing with arrangements of points in space.
Right.
And braid groups, which capture how you can intertwine strands.
It's like we've opened up this door into this huge landscape of mathematical ideas, with this Operad framework as our guide.
Yeah, for sure.
And as we venture further, I'm sure we'll keep finding those aha moments.
Right.
Those flashes of insight that connect those seemingly unrelated concepts.
Yeah. And those moments, that's what makes the pursuit of knowledge so rewarding.
I completely agree.
The beauty of mathematics lies in its ability to surprise us, to reveal those hidden patterns and unexpected symmetries. And as we've seen in this deep dive, the Operad approach is a powerful lens for viewing this intricate dance of particle interactions.
It's been so great exploring this topic with you. The source material, it's provided such a rich and stimulating foundation for this discussion. And I'm left with this, deep appreciation for the elegance and power of mathematical thinking.
Yeah, me too. It's been a really enlightening deep dive. It really showcases that ability of math to illuminate the world around us.
Yeah.
From those simplest interactions to the most complex structures.
And to our listeners out there, we encourage you to continue exploring this fascinating topic. Pick up a book, read a research paper, or just let your curiosity be your guide. You never know what amazing discoveries await.
Remember, even the most complex phenomena often have these really elegant mathematical underpinnings. And, pursuing and understanding those underpinnings, it's a rewarding journey, full of unexpected twists and turns.
So keep your minds open, embrace the power of abstraction, and let the beauty of math inspire you. Welcome to another deep dive. Today, we're going on a bit of a journey into the world of theoretical physics and mathematics. Specifically, we'll be exploring this paper on scattering diagrams and operads. It's titled Planar Rooted Line Arrangements and an Operad for Factorized Scattering. Sounds pretty complex, right? But I'm sure with your help, we can break it down and find some really interesting insights.
Absolutely. This paper delves into some fascinating concepts, exploring how we can visualize and analyze particle interactions using scattering diagrams and this powerful mathematical framework called operads.
Okay, so the paper starts by focusing on purely elastic scattering, both in classical and quantum systems. Can you remind us what makes elastic scattering so special, and why is it the focus of this paper?
Sure. In essence, elastic scattering is all about those perfectly bouncy collisions, where particles conserve both their total momentum and total kinetic energy throughout the interaction. It's kind of like billiard balls bouncing off each other on a perfectly frictionless table.
Right, so no energy is lost as heat or sound. It's a perfectly clean exchange of momentum.
Exactly. And this simplification lets us really focus on the geometric and combinatorial aspects of the scattering process. A crucial property highlighted in the paper is that in elastic scattering, particles never overtake each other. Their trajectories might intersect, but they always maintain a specific order, leading to some interesting geometric patterns in our scattering diagrams.
It's like there's a hidden order within the chaos of these collisions.
Precisely. And to visualize this order, the paper introduces the what they call the QT plane. It's like a stage where the horizontal axis represents time, denoted by T, and the vertical axis represents position, denoted by Q. Each line on this stage represents the asymptotic trajectory of a particle. Not its precise path, but the path it would take if the interaction didn't curve its trajectory.
So it's like a simplified map of the particle's journey, focusing on the long-term behavior rather than the nitty-gritty details of the collision itself.
That's a great way to think about it. Now, the paper mentions two ways of representing these scattering processes: reflection and transmission. In the reflection picture, you can imagine particles reflecting off each other, exchanging momenta, but keeping their identities.
Okay, so like those billiard balls bouncing back in opposite directions.
Exactly. But in the transmission picture, the particles essentially pass through each other, but their relative order changes due to the interaction. Each particle retains its original momentum, but picks up a phase shift, denoted by jor A, which represents a shift in its asymptotic position. It's as if they briefly traded places as they crossed paths.
So in the reflection picture, the momenta are swapped, while in the transmission picture, it's the positions that are affected. That's an interesting distinction. The paper then goes into some specific examples using these collidorer potentials. Could you explain what those represent and why they're chosen for these examples?
Certainly. Collidorer potentials describe specific types of interactions between particles. Their key feature is that they're impenetrable and repulsive, ensuring particles can never occupy the same point in space.
So it's like they have this force field around them, preventing them from ever overlapping.
Exactly. This property guarantees that our particles never truly overlap in the scattering diagram, even when their trajectories intersect. The paper focuses on rational and hyperbolic collidorer potentials, which are known for their elegant mathematical properties and their relevance to what we call integrable systems.
Okay, so we have our scattering diagrams, these special potentials setting the rules, and these two ways of visualizing the interactions, reflection and transmission. Now, where do these operads come into play? The term sounds a bit abstract and intimidating.
Operads, although they might sound a bit daunting, are really a powerful framework for fusing or composing these particle configurations. Think of them as a set of rules for combining simpler interactions to create more complex ones.
So instead of analyzing each collision in isolation, we can use operads to understand how these individual events combine to create a bigger picture.
Precisely. The beauty of operads lies in their structure and consistency. They give us this rigorous mathematical language to describe these composition operations. So no matter how we combine our configurations, the final result is well-defined and meaningful. And in the context of these scattering diagrams, we represent these compositions using what are called planar-rooted trees.
Trees, like the ones we see in nature.
Well, not exactly those kinds of trees, but the concept of branching and hierarchy is similar. Each node in our tree represents a particle configuration, and the branches show how these configurations are combined.
I see. So a simple collision will be represented by a basic tree with just a few branches, while a more complex interaction might involve a larger, more intricate tree.
You got it. And the paper emphasizes that this composition process is not commutative. The order in which we combine these configurations really matters. It's not like adding numbers. Swapping the order generally leads to a different outcome. We need to specify not just which configurations we're combining, but also what we call the insertion position, denoted by I. This tells us where on the first configuration we're grafting the second one.
So it's like a precise set of instructions for building our complex interactions step by step.
Exactly. Operads ensure that those instructions are always consistent no matter how complex our constructions become.
Now, the paper mentions this chronological symmetry. What does that mean in this context of composing particle configurations?
Ah, yes. The chronological symmetry. It refers to a key property of operads where the final configuration we obtain doesn't depend on the specific order in which we perform pairwise compositions. As long as, of course, the overall hierarchical structure of the tree remains the same.
So it's like saying that rearranging the order of individual steps in, let's say, building a Lego model, won't change the final model as long as we follow the overall blueprint.
That's a great analogy. Mathematically, this invariance is captured by the condition AEI-BEAJ plus I1C equals AEI-BHAC for 1 AJI. This essentially means that the final outcome should only depend on the overall structure of the interactions, not the specific order in which they occur.
Right. It ensures a certain level of robustness in our framework. But how do we actually apply these abstract concepts of operads to concrete examples? Does the paper give any specific instances of operads in action?
It does. The paper introduces several examples to illustrate how they work. One of the simplest is what we call the associative operad, denoted by as. In this operad, elements are represented by planar corollas, basically trees with a single internal node and multiple leaves. The key feature of as is that all its partial compositions are equivalent. It doesn't matter which leaf we attach a tree onto, the result is always the same. This property is reflected in the condition AEIB, AJ plus I1C equals AAI, BAs for 1S, BHII, which holds in as.
So it's like a fundamental building block for constructing more complex operads.
Exactly. It captures the essence of associativity, a core concept in many areas of mathematics and physics. From as, we can build more intricate operads. For example, what's called the word operad, denoted by WA. It's a simple extension of as where we decorate the leaves of the corollas with elements from a monoid.
Hold on, a monoid. Could you remind us what that is?
Of course. A monoid is a set equipped with an associative binary operation and an identity element. Think of it like a generalized version of multiplication on numbers.
Okay, that rings a bell. So in the word operad, we're adding some extra information to our basic associative structure.
Precisely. This extra information, represented by the elements of the monoid, allows us to represent more nuanced relationships between our particle configurations.
That's interesting. Now, are there any other types of operad? Does the paper explore any examples beyond associative and word operads?
It does. It also introduces the concept of endomorphism operads, denoted by end-V. These are particularly useful for representing an operad as an algebra acting on an object, which we'll call V.
Could you elaborate on that a bit? What does it mean for an operad to act on an object?
Imagine this. An endomorphism operad allows us to translate the abstract structure of an operad into a concrete set of operations on a specific object, V. It's like giving our Lego model a specific purpose or function within a larger system.
Okay, I'm starting to see the connection. So we're moving from abstract compositions to concrete actions on a specific object.
Exactly. And this connects nicely to the familiar notion of an associative algebra, which is essentially an endomorphism operad acting on a vector space.
That makes sense. Now, all these examples seem quite abstract, derived from mathematical principles. Are there any operads that arise more naturally from, let's say, geometric or physical systems? Operads that, so to speak, emerge organically from the world around us?
That's a great question. And yes, there are. The paper introduces a fascinating example. Tiling operads. These are operads derived from self-similar tilings of polyhedra.
Self-similar tilings? That sounds intriguing. Like fractals.
You got it. Think of shapes that can be repeatedly subdivided into smaller, identical copies of themselves. The classic example is the L-shaped tromino, which can tile a larger L-shaped tromino using 4 smaller copies.
Okay, I can visualize that.
Yeah.
But how do we get an operad from these tilings?
The key is to represent the process of tiling substitution using those planar rooted trees we talked about earlier. Each node of the tree represents a specific tiling, and the branches indicate how we substitute tiles with other tilings to create more complex patterns.
So we're building up these intricate tilings step by step, and the tree captures the hierarchy of those substitutions.
Precisely. The paper shows that these tiling operads can be represented as sub-operads of the word operad WG, where G is the group of admissible tile transformations. This connection provides a powerful link between the geometry of tilings and the algebraic structure of operads.
It's amazing how these seemingly different concepts, tilings and operads, can come together in such a harmonious way.
Indeed. And this is just the tip of the iceberg when it comes to the beauty and power of operads.
This is all incredibly fascinating. We've covered a lot of ground already, from the basics of elastic scattering to the abstract world of operads and their various manifestations. But I'm eager to delve deeper into the specific operad that lies at the heart of this paper, the line arrangement operad. I have a feeling things are about to get even more interesting.
You're absolutely right. That's where we'll pick up in the next part of our deep dive. The line arrangement operad is where things really start to connect, bridging the abstract framework of operads to the concrete geometry of scattering diagrams.
All right, let's dive into this line arrangement operad. It sounds like it's the key to connecting the abstract world of operads to those visual representations of particle interactions, those scattering diagrams we were discussing.
Exactly. The line arrangement operad, denoted by L, essentially takes those scattering diagrams and turns them into elements of an operad, which lets us compose and manipulate them in a structured way.
So instead of looking at individual scattering diagrams, we can start, combining them, like building more complex scenarios from simpler ones. But how do we actually represent these arrangements within an operad? What are the building blocks?
Well, each element in L is what we call a planar rooted line arrangement. Imagine you have a plane, and on this plane there's a distinguished horizontal line. We call this the root. And then we have other lines representing the particle trajectories that intersect this root. The root is given a direction, typically from left to right, and the other lines intersect the root in a specific order without any two lines being parallel. All those pairwise intersections have to lie in the upper half plane defined by the direction of the root.
Okay, I'm trying to visualize this. So the root is like the timeline of the interaction, and the other lines are the particles entering and leaving the scene.
That's a great way to think about it. It's like a well-organized freeway system where cars can merge onto the main road, but only in a very specific sequence, and no head-on collisions allowed.
Right. No crashes. But how do we compose these arrangements? How do we combine these freeway systems, so to speak?
That's where affine transformations come into play. Remember, affine transformations are those geometric transformations that preserve parallelism and ratios of distances.
Yeah, I vaguely remember those from geometry class, stretching, rotating, translating, all that.
Exactly. They can do all that while keeping those key geometric relationships intact. Now let's say we have two line arrangements, P and Q. To compose them, denoted by PIQ, we use a specific affine transformation, denoted by TU, to map a portion of Q onto a region of P. It's like merging sections of those freeway systems together.
Can we walk through that process? I want to make sure I understand how this merging actually happens.
Absolutely. Let's focus on P first. We're going to pick two adjacent lines in P, labeled pi and pi plus 1. We then look at their points of intersection with the root, which we'll denote as pi and pi plus 1 respectively. If we connect these 2 points on the root with a straight line, we can mark the point where this line intersects pi as pi plus 1. This gives us a nice triangular region in P, bounded by the root, pi, and that line connecting pi and pi plus 1.
Okay, so we've carved out a specific zone in P, like designating a section of our freeway for the merge.
Precisely. Now we do something similar with Q. We identify the first line, Q1, and the last line, QM plus 1 in Q, and their respective intersection points with the root, denoted as Q1 and QM plus 1. We connect these root points with a line and mark the point where this connecting line intersects Q1 as Q1 meter plus 1.
So we have another triangular region, this time in Q. I'm seeing a pattern here.
You're right on track. There's this unique affine transformation, T, that can map the triangle Q1 a meter plus 1, Q1 plus 1 in Q onto the triangle pi plus 1 in P.
So we're stretching, rotating, and translating that triangle in Q to fit perfectly onto the triangle in P.
Precisely. And because we're using an affine transformation, all the lines within that triangle in Q are mapped onto corresponding lines in the triangle in P, maintaining their relative arrangement. No collisions, just a smooth merge.
Okay, I'm visualizing it now. But what happens to the rest of Q? The lines outside of that triangle. We can't just discard them, right?
Of course not. Those lines outside the triangle in Q are also transformed by T, but they don't interfere with the existing lines in P. They create new intersections and expand the arrangement. It's like adding new lanes and exits to the freeway system.
That's clever. Seamless integration guided by this affine transformation.
Exactly. The final result, PQ, is a new planar-rooted line arrangement that's richer and more complex than either of the originals. And importantly, it still follows all the rules. No parallel lines, pairwise intersections in that upper half plane, and a specific order of intersections on the root.
Right, so no impossible freeway scenarios. That's reassuring. But this brings me to the idea of operads needing to be associative. How do we prove this associativity when we have all these affine transformations going on? It seems like things can get pretty messy.
That's where the paper gets into some really elegant math. They demonstrate that this composition with affine transformations does satisfy both the sequential and parallel associativity conditions, like proving that no matter how we group our freeway merges, as long as the sequence is the same, we end up with the same freeway system.
That makes sense intuitively.
Yeah.
But how do they actually prove this mathematically?
It's quite ingenious, really. They connect this line arrangement operad to the word operad, WG, which we talked about earlier. Remember how in the word operad, elements are words formed from letters in a monoid?
Vaguely, yes.
Well, the key insight here is that we can encode each line arrangement as a sequence of these affine transformations, each transformation representing a merging operation.
So we're translating geometry into this algebraic language of words.
Exactly, and this translation preserves the essential properties of the composition, allowing us to use the framework of word operads to prove associativity in the line arrangement operad.
That's a neat trick. By connecting those two seemingly different concepts, they've bridged the gap between geometry and algebra, giving us a solid foundation for our line arrangement operad.
Absolutely, and this connection has some far-reaching implications. It gives us the tools to analyze and manipulate those scattering diagrams in a really precise way.
Okay, so we've established that the line arrangement operad is a legitimate operad, with that affine transformation composition. But what else makes this operad special? Are there any unique properties that set it apart from others?
Oh, absolutely. One remarkable thing about L is that it can be generated by a surprisingly small set of building blocks. In addition to the symmetry group, L, which is just the group of affine transformations, we only need 3 topological families of binary operations to build any conceivable planar-rooted line arrangement.
Wait, just 3 families? That seems incredibly efficient. How can such a small set of operations give rise to such a vast variety of line arrangements?
The key is that we can build any complex arrangement step by step, adding lines one at a time, starting from just 2 lines. These 3 families of binary operations represent the 3 fundamental ways we can add a new line to an existing arrangement.
So it's like having a minimal set of rules for expanding our freeway system.
Exactly. It's incredibly simple, yet powerful. And by repeatedly applying these 3 basic rules, we can generate any planar-rooted line arrangement. This really highlights the elegance and efficiency of L. It speaks to the underlying order and structure that govern these seemingly chaotic scattering processes.
This is fascinating, but I'm still grappling with how this abstract operad connects to the concrete reality of particle scattering. How do we bridge that gap?
That's where the concept of a scattering theory comes in. In this context, a scattering theory is essentially an operad morphism from the line arrangement operad L to another operad, which we'll call P.
Okay, remind me, what's an operad morphism again?
Essentially, it's a map between 2 operads that preserves the structure of the composition. Think of it like a translator between 2 languages.
Got it. So we're mapping the structure of our line arrangement operad onto this other operad P. But what does P represent? What's the target language, so to speak?
P represents the space of possible outcomes of the scattering process. It could be information about the final momenta of the particles, their positions after the interaction, any other relevant physical properties. This morphism captures how the geometry of that initial line arrangement, which represents the incoming particles, dictates the final state, which is represented by an element in P.
Okay, so we're not just describing the geometry anymore. We're mapping it onto the actual physical consequences.
Precisely. But where does the concept of factorized scattering fit into this? Remember, that's where multi-particle interactions can be reduced to pairwise collisions.
Right, breaking down a complex problem into simpler pieces.
Exactly. And that's where Baxter's Z-symmetry comes in. It allows us to shift the lines in our scattering diagram without changing their order.
Yes, like rearranging the freeway lanes without changing the order of cars.
Exactly. Now, in a factorized scattering theory, the outcome of a multi-particle collision is determined by the outcomes of all the possible pairwise collisions. The paper shows that we can use the Z-symmetry to express this idea very elegantly using
between the geometry and that concept of factorized scattering.
Precisely. It allows us to transform any line arrangement into a configuration where all the lines intersect at a single point, effectively reducing the problem to a series of 2-body interactions.
That's brilliant. It makes the analysis much simpler.
Absolutely. And the paper demonstrates that a scattering theory satisfying the Yang-Baxter property, which is important for many integrable systems, basically factorizes through the Z-symmetry transformation. This means the outcome of the scattering is invariant under those Z-symmetry operations, highlighting the role of pairwise interactions in these systems.
Okay, I think I'm starting to see how all these pieces fit together. We have our line arrangement operad capturing the geometry. We have the idea of a scattering theory mapping this geometry onto the possible outcomes. And we have the Z-symmetry as this simplifying lens for analyzing those multi-particle interactions in the context of factorized scattering.
You've got it. It's a powerful framework for understanding the connection between geometry, algebra, and physics in the realm of particle scattering. And the paper even hints at deeper connections, linking these scattering diagrams to other fascinating structures like polytopes and the Swiss cheese operad.
Wow. It sounds like we've uncovered a whole network of interconnected concepts, each offering a different perspective on the same problem.
Exactly. It's a testament to the power of math to reveal these underlying patterns and connections. And, well, that's where we'll pick up next time. We'll explore how those scattering diagrams can be visualized as paths on polytopes and how their topological properties can be captured by that Swiss cheese operad. It's a journey that takes us from familiar geometry to the realm of topology and beyond.
All right, I'm ready for those polytopes in the Swiss cheese operad. They sound like they come from completely different areas of math. How do they connect to our scattering diagrams and the line arrangement operad?
It is quite remarkable how these different areas of math converge in this context. Let's start with polytopes, specifically something called permutahedra. Remember, our scattering diagrams show how particle positions change over time on that QT plane. If we freeze time for a moment, We get a snapshot of the particle's positions, like points on a line.
Right, a cross-section of the scattering diagram at a particular time,
Yeah.
capturing that instantaneous arrangement of the particles.
Exactly. Now, as the particles scatter and their positions change, we get different configurations of points on that line at different times. And we can represent these changing configurations using permutahedra. A permutahedron is a geometric object, and its vertices correspond to all the possible permutations of a set of elements.
So if we have, say, 3 particles, the permutahedron would have vertices for every possible ordering of those particles, like 123, 132, 2 and 13, and so on.
Precisely. There'd be 6 vertices in total, one for each permutation of those 3 elements. As our particles scatter and the positions change, we can actually trace a path along the edges of this permutahedron, moving from one vertex to another. This path represents how the particle configuration evolves over time.
So we're turning the time evolution of our scattering process into a journey through this permutahedron.
That's a great way to put it. The paper calls this path a polytopic chain, and it contains a lot of information about the scattering process. For example, if the scattering involves only pairwise collisions, that path sticks to the edges of the permutahedron. But if 3 or more particles collide at the same time, the path might take a shortcut through the interior of the permutahedron.
So the geometry of the path tells us about the complexity of the interactions. Simple pairwise collisions stay on the surface, while those more intricate multi-particle collisions go through the heart of the permutahedron.
Exactly. This link between scattering diagrams and permutahedra opens up some really exciting possibilities. We could use polytope theory to analyze these paths, maybe reveal some hidden symmetries or patterns in the scattering dynamics that aren't obvious just from the scattering diagram itself.
That's really cool. We've got this whole new geometric interpretation of our scattering diagrams, connecting them to these permutahedra and those polytopal chains.
Indeed. And this geometric perspective can even help us understand the Yang-Baxter equation. Remember, it plays a crucial role in factorized scattering theories. Well, the 2 sides of the Yang-Baxter equation can be interpreted as different paths on that permutahedron, starting and ending at the same vertices, but taking different routes.
So the Yang-Baxter equation, which governs the consistency of factorized scattering, has a geometric representation in the world of permutahedra. That's amazing.
It really highlights the deep connections between these different ideas. Now, let's shift gears a bit and talk about the Swiss cheese operad, which brings in topology.
Okay, I'm intrigued. Swiss cheese operad is a pretty interesting name. What does cheese have to do with scattering diagrams?
It's all about visualizing the topological structure of the scattering process. Remember, those lines in a scattering diagram represent the asymptotic trajectories of the particles, and the intersections represent those collisions.
Right, a roadmap of the particles' journeys.
Now imagine focusing on the upper envelope of this line arrangement. That's the polygonal chain that traces the outermost edges of the diagram, connecting the points where those lines intersect the root. It's like the outline of the scattering process.
Okay, so outlining the boundary where the scattering happens.
Exactly. The key idea is that we can thicken this upper envelope, replacing each line segment with a thin rectangular band. We can then smooth out the corners, and the resulting shape looks a lot like a half disc with some smaller half discs cut out from its bottom edge.
Ah, I see it now. It really does look like a slice of Swiss cheese. Those holes representing the spaces between the lines in the scattering diagram.
Precisely. These Swiss cheese shapes, with different numbers of holes and cutouts, form the elements of the Swiss cheese operad, denoted as SC.
Okay, so we turned our scattering diagram into this topological Swiss cheese object. But what's the point of this transformation? What does this cheese perspective tell us?
The Swiss cheese operad captures information about the connected components of the complement of the line arrangement. Each hole in the Swiss cheese represents a region that's enclosed by the lines of the scattering diagram. It's like looking at the negative space between those particle trajectories.
So now we're not just looking at the particles' paths, but also the spaces they create as they interact.
Exactly. This shift in focus allows us to connect these scattering diagrams to a whole bunch of topological tools. We can study the homotopy type of these objects, analyze their homology groups, and explore how they relate to other topological operads.
It's like we've opened a door from particle physics into the world of topology.
Precisely. And the paper suggests this could be a very fruitful connection. For instance, we might be able to classify different scattering diagrams based on the topological features of their corresponding Swiss cheese representations, or we could use topological tools to study how scattering processes deform or change when we introduce perturbations.
Wow, the possibilities are pretty exciting. It's amazing how something as simple as a scattering diagram can lead us to such a wide range of mathematical ideas.
It really speaks to the power of mathematical abstraction. By stripping away the specific details, we uncover this profound underlying structure, connecting geometry, algebra, combinatorics, and topology, giving us a deeper, more unified understanding of these particle interactions.
It's like we've found this hidden blueprint, written in the language of mathematics. Well, listeners, we've come to the end of our deep dive into scattering diagrams and operads. Hope you enjoyed exploring this fascinating world with us.
It's been a fascinating journey from those simple billiard ball collisions to the abstract world of operads, polytopes, and even topological cheese. Along the way, we saw how these concepts are interconnected and how they help us illuminate the fundamental processes of our universe.
If you're feeling inspired, we encourage you to explore further, dive into those references from the paper, and embark on your own mathematical adventures. Who knows what you might discover? Until next time, keep exploring, keep questioning, and keep diving deep into the wonders of the world around us. Welcome to another deep dive, and this time, we're diving headfirst into the world of scattering diagrams and operads.
Yes.
I've been looking over the material you sent, and it's quite fascinating. I mean, we're basically going to be exploring these scattering diagrams, which, as I understand it, they kind of show how particles interact, right? And then there's this whole connection to operads, which,
absolutely,
to be honest, it's a little intimidating, but I'm definitely eager to unpack all of this with you.
That's the heart of this deep dive. What's really cool is how we start with, well, it's a system that sounds pretty simple, purely elastic scattering in 1 + 1 dimensions. And it takes us to some pretty high-level math. Yeah.
Before we get too deep into those complexities, though, could you just remind us what purely elastic scattering actually means? Why is it so important for this particular deep dive?
So in purely elastic scattering, the particles, they maintain their incoming and outgoing momentum sets. Basically, when they interact, they're just exchanging momentum. No energy's lost in the process.
Well,
it's like, imagine those billiard balls colliding perfectly on a frictionless table.
Right. A classic example.
Yeah.
The paper mentioned asymptotically free zones, too.
Yes.
What's the significance of those?
They're very important because they represent regions where particles are essentially on their own, uninfluenced by other particles.
Okay, so they're free and zero?
They're only influenced when their paths intersect.
I gotcha.
The rational and hyperbolic Colligero-Moser potentials are great examples of systems that behave like this.
Gotcha. So you're saying the particles only interact significantly when they're really close?
That's it. And these Colligero-Moser potentials, they decay very rapidly with distance.
Okay, that makes sense.
So yeah, they make it much easier to study these scattering phenomena because of that. And one more thing about them, they're impenetrable.
Okay.
Which means particles can't be in the same position at the same time. So that leads to these well-defined interactions.
I see.
Yeah.
Okay. This whole idea of using line arrangements, to represent how particles move.
Right.
That's pretty cool.
It is.
Visually.
Yeah.
Can you connect that to these scattering diagrams?
Absolutely. So think of each line in the arrangement as a particle's trajectory through space and time.
Okay.
The slope of the line, that represents its momentum. And when those lines intersect, well, that's when the particles interact.
Got it.
But keep in mind, these diagrams, they're not meant to be literal depictions of trajectories.
Okay.
They're more about capturing the crucial information when and how the particles interact.
Right. The essence of the interaction.
Yeah.
So the paper mentioned these reflection and transmission presentations.
Yeah.
What do those mean in this context?
Okay. So the reflection presentation focuses on how particles' momenta change when they interact.
Okay.
Just like those billiard balls changing direction.
Got it.
But then you have the transmission presentation, where particles actually pass through each other. They keep their original momenta, but their order changes.
I see.
And there might even be a phase shift, denoted by Hei, which quantifies the effect of the interaction.
So they kind of swap places, but they carry this, memory of their encounter. Sounds like we're dealing with systems where the order of those particles really matters.
Precisely.
Okay, so how do we even begin to combine these scattering diagrams? I mean, that's where operads come in, right?
Absolutely.
But what are operads? Can you explain them in a way that even someone who's not a mathematician can understand?
Sure. An operad gives us a structured way to combine and compose objects.
Okay.
Imagine you have these building blocks and specific rules for connecting them.
Okay.
That's the basic idea.
I get it.
A good analogy is grafting trees together.
Grafting trees. Okay, I'm listening.
So think of each branch of a tree as representing a particle's trajectory. When you graft, you're connecting those smaller trees into bigger ones, representing how multiple scattering processes combine.
Okay.
And those operad rules, they make sure those combined diagrams make sense.
Okay.
They're consistent.
It sounds like operads are like a set of rules that guarantee we're not breaking the laws of physics when we combine these scattering diagrams.
Right, exactly.
Can you give us some examples of operads, like, specific types?
Absolutely. One example is the associative operad. It's denoted as.
Okay.
And this one governs how we multiply numbers or combine objects associatively.
Okay.
So, like, it doesn't matter if you do 1 + 2 + 3
Right.
or 1 + 2 + 3, you get the same answer.
Right. The order doesn't matter. That makes sense. What are some other types?
There's also the word operad. So you think of words as composed of letters.
Word operad, huh? What's that about?
The word operad dictates how those words combine.
So like how you can insert one word into another.
Exactly.
Yeah.
Maybe at a specific position. Like if you had the words cat and dog,
Okay.
you might get cadocked.
Okay, that's cool. What about some visual examples? Something more like our scattering diagram.
Wait, there's the little one-discs operad. It's similar to the associative operad,
Okay.
but instead of numbers, it combines line segments within a unit interval.
Okay.
So you have these sets of line segments, and the operad's rules tell you how to merge them into a new set,
Gotcha.
all within that same interval. It's quite relevant to studying the combinatorics of scattering diagrams.
Right.
So like, it's almost like we're taking those line segments representing our particles and kind of merging their paths in a way that makes sense.
Exactly. These examples show how operads, even though they can seem pretty abstract, they have all sorts of applications.
Yeah, definitely.
They're pretty powerful tools.
Okay. Now, I'm kind of curious about how we go from like these abstract trees, these line segments, to real scattering diagrams.
Right. How does this operad framework actually help us build up more complex scattering scenarios?
That's where the paper dives into two different ways to construct operad structures on planar-rooted line arrangements.
Okay.
So construction focuses on what we call decoupling the positions and momenta of the particles.
Decoupling positions and momenta.
Yeah, so it means we treat them as independent things when we're defining the operations in our operad. This gives us an operad structure that's actually isomorphic to the product of two configuration space operads, one for positions and one for momenta.
Okay, so we're essentially building these complex scattering scenarios by sort of piecing together the positions and momenta of particles from simpler scenarios separately.
Exactly.
Okay.
It's a really structured way to build up complexity. Then you have construction 2, which takes a more geometric approach.
Okay, tell me more about construction 2.
Sure. So construction 2 uses something called the affine symmetry group of the plane,
Okay.
which is basically all the transformations that preserve straight lines and parallelism. Okay.
Remember those transformations, Steve, that map triples of points between arrangements?
Yeah, those were important for like merging the line arrangements, right?
Exactly.
Making sure their geometric features were preserved.
Precisely.
Okay.
So construction 2 utilizes those transformations to define an operad,
Okay.
where the composition of those arrangements respects the geometric relationships between the lines.
So it's all about keeping the geometry consistent.
Exactly. And it introduces this concept of a moving frame, which is really neat.
A moving frame. Okay, what's that about?
Think of it as a convenient coordinate system that's tailored to the object or system you're studying. Like if you're describing a car's motion, you could use a fixed coordinate system, like a city map.
Okay.
Or you could use a coordinate system that moves with the car.
Gotcha. So it's all about choosing the right coordinate system to make things easier to understand.
Exactly.
But how does that apply to these scattering diagrams? So in construction 2, the moving frame helps us normalize the line arrangements before we combine them.
Normalize.
We basically define what we call normalized arrangements.
Yep.
Within a specific triangle, bounded by the lines t equals 0, q equals 0, and q plus t equals 1.
Okay.
So we're shifting and scaling things to fit within this triangle before we combine them.
I see.
And the cool thing is once we've combined them, we can use the moving frame to transform them back to any frame of reference we want.
That's really clever. It's like having a universal translator for scattering diagrams.
Exactly. And it gives us a much deeper understanding of the structure of these systems.
Okay, that's really fascinating.
Yeah.
But I'm still wondering, what's the point of combining these scattering diagrams?
Right.
Like, why is it important? And what do we learn by using Operads to study them?
One of the key things we learn about is the inherent symmetries within these scattering processes. Remember Z-symmetry?
Yeah, that was about how you can shift the lines without changing the actual scattering information, right?
Exactly. So Z-symmetry plays a crucial role in understanding something called factorized scattering.
Okay.
The Operad structure helps us see how Z-symmetry connects different scattering diagrams.
I see.
Any scattering diagram can be transformed, using Z-symmetry, into a configuration where all the lines intersect at a single point.
Okay, so no matter how complex the diagram starts out, we can simplify it down to, like, a single point where all the action happens.
That's the idea. And this transformation is actually what we call a surjective Operad morphism.
Yeah.
It maps a more complex scenario onto a simpler one while preserving the Operad structure.
Gotcha. So it's like it shows that these different scattering scenarios might look different, but they actually share a common underlying structure.
Exactly. And that structure is governed by the Operad.
Okay.
It's really pretty neat.
So to be sure I understand, we have these scattering diagrams that we can combine using these Operad rules. Yeah. Then we can use Z-symmetry to make any of these diagrams simpler.
Right.
By making all the lines intersect at one point.
Precisely.
And this simplification, it's an Operad morphism because it preserves the structure.
That's it. And what this morphism tells us is that there's a deeper relationship between all these different scattering scenarios. They might seem different on the surface, but they're all connected by this underlying structure governed by the Operad.
That's pretty remarkable. It's like we're looking into the heart of these scattering processes and finding this like hidden order that connects them all.
That's a great way to put it. And this is just the beginning. The Operad framework gives us this powerful lens for exploring symmetries and relationships within these processes.
Okay, cool.
Leading to a deeper understanding of the math behind them.
That makes sense.
Yeah.
So before we dive into factorized scattering,
sure.
Could you talk a little bit more about the whole moving frame concept?
Of course.
I'm not totally clear on how that works and why it's so important.
Okay, so a moving frame is essentially a convenient coordinate system, or you could say a reference frame, that's tailored specifically to whatever you're studying.
Yeah.
So let's say you're describing how a car moves.
Okay.
You could use a fixed coordinate system, like a city map.
Right.
Or you could use a coordinate system that moves along with the car, focusing on its position and orientation relative to its path.
I see.
That's the essence of a moving frame.
Got it. So it's about choosing the coordinate system that makes the analysis simpler.
Exactly.
But how does that actually work with these scattering diagrams?
So in construction 2, we use this moving frame to normalize the line arrangements before we combine them.
Okay.
We define what we call normalized arrangements within this unit triangle.
Okay.
Bounded by the lines t equals 0, q 0, and q plus t also 1. This normalization, it's done by choosing a specific moving frame.
So it's like we're shifting and scaling the arrangements to make them fit within this specific triangle before we combine them.
Precisely. And the beauty of it is once they're combined, we can use that moving frame to transform them back to any frame of reference we need.
Wow, that's pretty elegant. It's like a universal translator for scattering diagrams.
That's a great analogy.
So it seems like we're getting a much deeper understanding of how these systems work by working with these simplified representations, right?
Absolutely. And that understanding of the structure is really what paves the way for exploring this concept of factorized scattering.
Okay.
And its connection to the Operad framework.
All right. I'm ready for that.
Okay, great. Welcome back to our deep dive. Before the break, we were really getting into factorized scattering and how it connects to Operads. These Operad morphisms, they're like, I don't know, they're like Rosetta Stones for these particle interactions.
Yeah, they're pretty amazing.
They convert the scattering diagrams into outcomes while still keeping the math consistent.
Yeah, it's elegant.
It is very elegant. It's like having a universal translator, but for the language of particle interactions.
Right, exactly. Now, the paper mentions this connection to the Yang-Baxter equation.
Yes.
That name always makes me a bit nervous, to be honest.
Yeah.
Can we break that down a bit? Like, what is it and why is it important here?
Of course. At its core, the Yang-Baxter equation is about a very simple idea. In certain systems, the order in which interactions happen doesn't change the final outcome.
Okay.
It's a condition for what we call integrability.
Okay.
It helps us identify systems with well-behaved and predictable dynamics.
So, like, if we have particles A, B, and C, it doesn't matter if A interacts with B first and then C, or if B interacts with C first and then A.
Exactly.
The end result is the same.
The final outcome is the same, yeah. And the Yang-Baxter equation gives us a way to check this mathematically using something called an R matrix.
Okay, and what's an R matrix?
Think of it like a rule book for how those two particles interact.
Gotcha. So the Yang-Baxter equation is basically saying that if you combine these R matrices in different ways, representing different interaction orders, you should still get a consistent result.
Precisely.
Okay, so how does all of this connect back to our Operads and scattering diagrams?
Remember how Z-symmetry lets us transform any scattering diagram into a configuration where all the lines meet at one point?
Right. We can simplify the diagrams without losing any of the important information about the scattering.
That's key here.
Okay.
Scattering theories that satisfy the Yang-Baxter equation, meaning those where the interaction order doesn't matter, are precisely those that factorize through that Z-symmetry transformation.
Okay, so let me see if I've got this straight. We have these scattering diagrams representing particle interactions. We can simplify them using Z-symmetry to create diagrams where all the lines intersect at a single point.
Right.
And if our scattering theory follows the Yang-Baxter equation, meaning the order of interactions doesn't matter,
Right.
we can basically reduce any complex scattering process to a combination of these simpler single-point interactions. Is that right?
You've got it. Connecting the Yang-Baxter equation to the Operad framework really illuminates why factorized scattering works.
Okay.
It's a consequence of that underlying symmetry. It lets us break down these complex interactions into simpler pieces.
So the Yang-Baxter equation, Z-symmetry, and the Operad structure, they're all working together to reveal this hidden order within these factorized scattering systems. It's pretty amazing how these different concepts are all intertwined.
It is, yeah. It's a beautiful connection.
The paper also hints at some ways to extend these ideas even further.
Yes.
What are some of those possibilities?
One interesting direction is to think about scattering theories where the target operad, P, is valued in a category with what we call good homotopy properties.
Good homotopy properties.
Yeah.
Okay, I'm going to need a little help with that one. What does that even mean, and why would we want our target operad to be valued in such a category?
So homotopy theory deals with continuous deformations and equivalence relations between spaces. A category with good homotopy properties is basically one where those concepts are well-defined and behave in a, in a nice way.
Okay, so it's like a category where we can smoothly deform objects without, like, breaking them.
Exactly.
But why is that important for our target operad?
Remember that our operad morphism, S, maps those scattering diagrams to outcomes. Sometimes those outcomes might not represent just a single state, but rather a whole family of states that are continuously connected.
So instead of mapping to a single point, we're mapping to, like, a region representing a range of possible outcomes.
Exactly.
Okay, that makes sense. So using a target operad valued in a category with these good homotopy properties gives us a more flexible framework.
Right.
It acknowledges that there's some inherent uncertainty in these physical systems.
Precisely. It allows for a more nuanced representation of the scattering outcomes.
Yeah, I like that. It seems like a more realistic approach.
It is, yeah. More robust, you could say.
What other potential extensions did the paper mention?
Another really interesting idea is to modify the source operad, L itself.
Okay.
Remember how we defined L as that operad of planar-rooted line arrangements? Well, the paper suggests exploring alternative operads based on something called pseudoline arrangements.
Pseudoline arrangements. What are those, and how would they change our understanding of scattering?
Imagine a network of roads that can bend, but they never cross over.
Yeah.
That's basically what a pseudoline arrangement is.
So it's like a more flexible version of our line arrangements, where the trajectories can be curved.
Exactly. And using them as the basis for our operad could let us model more complex scattering scenarios where those particle trajectories aren't just straight lines.
So we could incorporate things like particle acceleration or even curved space-time?
Precisely. It's like moving from a flat world to a world with curves and bends, adding a whole new layer of complexity to our understanding of scattering.
That's a great way to put it. So by using these pseudoline arrangements, we can potentially study scattering in more realistic physical settings.
Exactly. It opens up a whole new range of possibilities.
Okay, that's really exciting. It's amazing how these abstract mathematical structures can provide such powerful tools for understanding physics.
It is, yeah. The interplay between the two is truly remarkable.
The paper also mentioned connecting these ideas to combinatorial and algebraic invariants of line arrangements and configuration spaces. Can you explain what those are and how they fit into this picture?
Sure. So in mathematics, invariants are objects that don't change under certain transformations.
Okay.
Like, for example, the number of sides of a square.
Okay.
That's an invariant under rotations. No matter how you rotate it, it still has 4 sides.
Right, it's a fundamental property that doesn't change.
Exactly. And in the context of line arrangements and configuration spaces, there are all sorts of interesting invariants that have been studied.
Okay, what kind of invariance?
Like, for instance, the number of regions created by a line arrangement.
Okay, so how many different areas those intersecting lines create?
Precisely. It's like looking at a city map and counting the blocks formed by the streets.
I get it. So can we use this Operad framework to study these invariants, maybe even discover new ones?
Exactly. Those Z-symmetry transformations, they can be used to simplify the calculation of these invariants.
Okay, so by using Z-symmetry, we can reduce the complexity of our line arrangements, making it easier to count those regions or intersections.
Exactly. And the Operads structure gives us a framework for understanding how these simplifications work and how they connect different line arrangements.
So it's like we have this powerful toolkit for exploring the geometry of these scattering diagrams.
Right.
And we can uncover hidden patterns within those complex configurations of lines.
Exactly. Connecting these ideas to invariant theory can give us a much deeper understanding of the underlying mathematical structure of these systems.
Okay.
And it could even lead to the discovery of new mathematical concepts.
This is really fascinating stuff. It feels like we're on the verge of some major breakthroughs in understanding scattering and its connection to mathematics in general.
It's an exciting time for sure.
It is. But before we get lost in all the possibilities,
Yeah.
I think it's a good time to pause again and let our listeners process all this incredible information.
So
We'll be back soon for the final part of our deep dive, where we'll explore even more amazing insights and potential applications of this Operad framework.
I'm looking forward to it.
Welcome back to our deep dive into scattering, diagrams, and operads. We've been on quite a journey exploring everything from the basics of factorized scattering to some pretty mind-bending connections with Z-symmetry, the Yang-Baxter equation, and even dipping our toes into homotopy theory and pseudoline arrangements.
It has been quite a journey. We've really seen the power of these, well, they might seem like abstract mathematical concepts, but they give us this framework for understanding the intricacies of particle interactions.
Oh, absolutely. It's been fascinating. Now, the paper also brings up a connection to polytopes.
Yes.
You know, those geometric shapes with flat faces and straight edges.
Right.
To be honest, that seems like another jump into the abstract to me. Yeah. How do these shapes relate to, what we've been talking about with particle interactions?
The key here is the transmission presentation of scattering, where particles kind of pass through each other and change their order. Remember those phase shifts? And how the order of the particles can change during interactions?
Yeah, the transmission presentation definitely gave us a different way to look at those interactions. It focused on how their order changes, not just their momenta.
Exactly. Now imagine you have, let's say, n particles moving on a line.
Right.
We can represent their initial order using a permutation of the numbers 1 through n.
Okay.
So, for example, if we have 3 particles, the initial order could be 1, 2, 3, meaning particle 1 is first, then particle 2, then particle 3.
So we're basically giving each particle a number based on its starting position.
Precisely. And as those particles interact, they pass through each other, their order changes.
Okay.
You get a new permutation. So if particle 2 overtakes particle 1, the new order might be 2, 1, 3.
So every interaction kind of shuffles the order of our numbered particles, creating a new permutation. It's like a dance where the partners keep switching places.
That's a great analogy. And here's the interesting part. The set of all possible permutations for realm particles can actually be represented by a geometric object called a permutahedron.
A permutahedron? What does that even look like?
For n particles, the permutahedron is an n1-dimensional polytope. The vertices of this polytope, they correspond to all the possible permutations of our particles.
Okay.
So for 3 particles, the permutahedron is a hexagon.
So each corner of the hexagon represents a different order of those three particles.
Exactly. And the edges of the hexagon, they represent transitions between those orders, corresponding to two-particle interactions.
So it's like our scattering process is a path that we trace on this permutahedron.
Yes.
We start at a vertex representing the initial order, and then we move along the edges as particles interact and change their order.
Exactly. The specific path we trace depends on, well, the specifics of the scattering process, which particles interact, when they interact, and the outcomes of those interactions.
Our scattering diagram, it becomes like this geometric journey on this permutahedron. It's a really visual way to capture how those particle orders change over time.
Precisely. And what's really neat is that this connection to polytopes lets us use a whole new set of mathematical tools to analyze scattering.
Like what kind of tools?
Well, polytope theory is a very rich area of mathematics with connections to, geometry, combinatorics, algebra. We can use tools from this theory to study the properties of those paths we trace on the permutahedron. Things like their lengths, the regions they enclose, all sorts of things.
So we can use the geometry of this permutahedron to really understand the dynamics of our scattering process.
Exactly. And this can lead to new ways of classifying those scattering processes, understanding their symmetries, and maybe even finding new invariants.
This is really fascinating stuff. I mean, we've gone from particle interactions to operads to polytopes. It's amazing how interconnected it all is.
It really is.
But before we wrap things up, I wanted to leave our listeners with something to ponder. We spent all this time talking about purely elastic scattering in 1+1 dimensions, where particles keep their momenta and energy is conserved. But what happens when we start thinking about higher dimensions?
Yeah.
Or inelastic scattering, where energy can be lost or gained?
That's a great question.
Does this operad framework still apply? And if it does, what new insights can it give us?
Those are questions researchers are really grappling with right now. Extending these ideas to higher dimensions and inelastic scattering, well, it's definitely a challenge, but it's also a huge opportunity.
Right.
Could it really change how we understand particle interactions? It's like, oh, we're exploring this uncharted mathematical territory.
It's exciting.
It is.
Well, this has been an amazing deep dive. We've journeyed from the very concrete world of particle interactions to this abstract world of operads, polytopes, homotopy theory. It's been quite a ride.
It has.
I want to thank you for joining us on this deep dive into the fascinating world of scattering diagrams and operads.
It's been a pleasure.
And to our listeners, keep those minds curious and engaged. We'll see you next time. All right, welcome back, everyone. Today we're going to be doing a deep dive into theoretical physics, but with a twist.
Yeah, it's a pretty heavy dose of math this time.
Exactly. We're talking scattering diagrams and operads.
Yeah.
How they relate, what we can learn from them. And you sent us a research paper.
Oh, yeah. This one's a doozy. Lots to unpack.
No kidding. Planar rooted line arrangements and an operad for factorized scattering.
So let's just jump right in. The paper kicks off by looking at a very specific physical system.
Right. Identical particles all on a line, and they're repelling each other. Kind of like
cars on a single-lane highway, all trying not to crash.
Exactly. And, it specifically mentions systems like the Killigero-Moser system. Those are known to be integrable.
Meaning we can actually solve their equations of motion, get those exact solutions.
Yeah, which is, really important here. Lets us analyze exactly how those particles behave. Okay, so we've got these particles, and they exhibit what's called asymptotic freedom, right? Essentially, they're just ignoring each other when they're far apart.
Pretty much, yeah. That's crucial because it means we can characterize them by their momenta, both incoming and outgoing, as if the interactions are super localized in time.
Like we can take a before and after picture of their momentum.
Right.
Okay, so where do scattering diagrams fit into all this? The paper's full of them. But I'll be honest, it took me a while to grasp what they're actually showing.
Yeah, they can be a little tricky to wrap your head around at first. The key is to remember those lines. They aren't showing the actual paths of the particles.
They're more like guidelines, right?
Exactly. Asymptotes, really. Lines that represent the particle momenta if there were no interactions at all.
Okay, so a simplified view, but one that still captures the core information about their motion.
Precisely. And the paper looks at two main ways to present these diagrams. You've got the reflection presentation, showing initial positions and momenta, and then the transmission presentation, which focuses on how their order and momenta change during the scattering itself.
Ah, so the reflection presentation is like the setup, and the transmission presentation zooms in on the action.
Exactly. And in that transmission picture, we also run into this concept of phase shifts.
Oh, right. I remember that term. They represent like small adjustments to the final positions of the particles compared to where they would have been if they hadn't scattered at all, right?
Right. It's a way to quantify the impact of those interactions.
Interesting. So these diagrams are really packed with information. But let's get to the heart of the paper here, the connection to operads. Why do we even need operads in this context?
Well, the paper's really focused on integrable systems, systems where these complex multi-particle scatterings can be broken down into a series of simpler two-body interactions.
Factorized scattering.
Exactly. But the question is, how do we actually describe that process formally? How do we combine those particle configurations in a way that makes sense?
You can't just use simple set unions, right?
Yeah.
You need to maintain that order of momenta and prevent any, like, unphysical overlaps.
Right. And that's where operads come in.
Okay, but for those of us who aren't, math whizzes, could you unpack that a little? What are they really?
Think of them like a set of rules for combining objects. But the key is, these rules, they have to be consistent, they have to be meaningful.
So in our case, the objects are those particle configurations.
Right. And the rules ensure that when we combine them, we're respecting the physics of the scattering process.
Okay, so operads are like a blueprint for building those scattering events, making sure everything fits together the way it should.
Exactly. Now, to actually use operads with these scattering diagrams, we need a way to represent particle configurations as elements of an operad.
And that's where those planar rooted line arrangements, or PRLAs, come into play.
Right. They give us this elegant geometric way to encode both the positions and the momenta of the particles.
PRLAs. So how are they defined, and how do they map onto these scattering diagrams?
Well, formally, you start with a horizontal line called the root line.
Which represents our one-dimensional space.
Exactly, at time 0. Then we add more lines, each one representing a particle's world line asymptote in that transmission picture.
So each line is the path a particle would take if it didn't interact with any others.
Right. Now, there are 3 key conditions for a collection of lines to be a PRLA. First, no 2 lines can be parallel.
Makes sense. If they were parallel, it'd mean 2 particles have the same momentum.
Exactly. Second, all interceptions between the non-root lines, they have to occur in the upper half plane.
The region above the root line.
Right. That's how we encode the order of their momenta.
It's like those lines are playing a game of Red Rover, and the root line is the dividing line. They can only cross above it. Okay, what's the third condition?
Third condition ties the arrangement to the actual order of the particles. The order in which the lines intersect that root line, it has to match the order of their indices.
So each line gets a number, and that number tells us where it hits the root line.
Exactly. It's a very structured system. And that structure is exactly what allows us to connect these PRLAs to operads.
The paper goes on to construct this operad, denoted L hat, where each element is a PRLA. So we're taking those carefully arranged lines and saying they can be the building blocks of an operad.
That's right.
How does that work?
Well, the key is defining how we combine those PRLAs. It's done through an operation called partial composition. Given 2 PRLAs P and Q, the partial composition, denoted PIQ, means we're inserting a rescaled and a finely transformed copy of Q between the ith and I+1 lines of P.
Okay, so we're not just, like, smashing them together. We're very carefully inserting one into a specific spot and the other, making sure to adjust the size and shape so it all fits.
Exactly. And this operation is designed so that the result still satisfies all those conditions of a PRLA.
Huh.
It's a really nice example of how we can use geometry to capture the rules for combining these configurations.
It is pretty elegant, but this operad L hat, it's not just about combining things, right? The paper dives into some of its properties, in particular, symmetries.
You got it. Symmetries are super important in both math and physics. And L hat has a bunch of key symmetries that reflect the underlying structure of the scattering system.
Okay, so break down those symmetries for us. What are the most important ones to understand?
Well, first, you've got the global gauge action. That lets us apply any affine transformation to the whole PRLA. Basically, we can move it, stretch it, rotate it, and the underlying physics doesn't change.
So it's like we can view our particle arrangement from different perspectives without changing the relationships between the particles.
Exactly. Then we have translations along the y-axis. This means we can shift all the particles by the same amount, and the scattering dynamics stay the same. It's all about the relative positions, not their absolute location.
Okay, that makes sense. What other symmetries are there?
Well, you've got p-symmetry and t-symmetry. Those correspond to flipping the diagram about the t-axis and the q-axis, respectively. They represent parity and time reversal symmetry.
So we can flip the diagram horizontally or vertically, and the physics stays the same. That's pretty cool. But I have a feeling you saved the best symmetry for last, didn't you?
You bet. There's one more that's super important, z-symmetry. This one's a bit more subtle. It lets us shift lines parallel to themselves without changing the order of the particle's momenta.
So we can slide those lines around as long as we keep their relative order along the root line the same.
Exactly. And this is where things get really interesting. Z-symmetry lets us transform any PRLA into a configuration where all the lines intersect at a single point.
Wait, so we can take this complex arrangement, all these particles scattering everywhere, and just collapse it down to a single point.
That's the power of Z-symmetry. It tells us the scattering dynamics only depend on the relative positions of the particles, not their absolute positions.
Wow, that's a pretty big simplification.
Right. And it leads to this remarkable connection. The sub-operad, denoted LA, which contains all those PRLAs intersecting at a point A, is isomorphic to the operad of static configurations.
So thanks to Z-symmetry, we can study scattering by looking at much simpler static arrangements.
You got it.
That is amazing. We started with particles on a line, went through all these intricate geometric constructions, and now we've landed at a place where we can study scattering in terms of static arrangements. Who knew symmetry could be so powerful?
It really is one of the most fundamental concepts in physics, but we've only just begun to explore the implications of this connection between scattering diagrams and operads.
Okay, you've definitely got me hooked. This is a deep dive I'm glad we're taking. What's next on the agenda?
Next, we're going to delve deeper into the concept of scattering theories themselves. We'll see how this operatic framework helps us define and understand them.
Okay, sounds good.
The Yang-Baxter property will come into play too, and that's where things get even more fascinating.
All right, I can't wait.
All right, so we're picking back up on our exploration of scattering diagrams and operads, and now we're going to dive into scattering theories themselves.
Okay, yeah, I'm ready for this. We laid all that groundwork with the PRLAs and the operad L-hat, all those symmetries.
Right.
But how do we actually use this whole framework to describe, the real nitty-gritty physics of particle scattering?
That's the million-dollar question. And scattering theories, they give us the answer. They're how we assign specific scattering data to each of those PRLAs, quantify the outcome of the whole process.
Okay, so each of those line arrangements, those snapshots of the particle interactions, now get a label that tells us something specific about how those particles scattered. What kind of information are we talking about here?
Well, it really depends on the system and what we're trying to learn. Could be phase shifts, transition amplitudes if we're talking quantum mechanics, or other quantities that capture the important parts of the interaction.
So we're translating the geometry of those PRLAs into physics language, using actual values or mathematical objects to describe the outcome.
You got it. Now, in the language of operads, a scattering theory is defined as an operad morphism from L-hat to some other operad, which we'll call P.
So we're mapping those PRLAs, which represent the particle configurations, to elements of another operad that holds the information about how they actually scatter.
Right, like a dictionary, translating between the geometry and the physics.
Okay, that makes sense.
And, the structure of P, it'll vary depending on what we want to capture. If we're dealing with quantum scattering, for example, P might be an operad where the elements are matrices. Those represent the transition amplitudes,
which give us the probabilities of different scattering outcomes.
Exactly.
So the target operad is really tailored to the specific type of physics we're after.
It's a flexible system. Now, remember that key lemma we talked about earlier?
Yeah, it said that to define this operad morphism, we only need to specify how it acts on PRLAs of ranks 2 and 3.
Right, because all those higher rank PRLAs, we can build them up by composing these simpler ones.
It's like we've got the basic building blocks, and once we know how they interact, we can figure out anything more complex.
Exactly. For rank 2 PRLAs, those represent two-particle scattering, right? We need to map those to elements of P1, which is the arity-1 component of our target operad.
And L-hat 1 is just our affine symmetry group G. So P1 has to be able to handle the symmetries of our system.
You got it. Now, rank 3 PRLAs, that's where things get a little more interesting. To keep things simple, let's just focus on scattering theories that respect z-symmetry.
Okay, hold on. Let's back up for a second. What does it actually mean for a scattering theory to respect z-symmetry? I get it for PRLAs, but how does it apply to the theories themselves?
Good question. It means that the scattering theory, it treats PRLAs that are related by z transformations as equivalent. So the scattering data we assign to them, it should be the same.
Ah, so it's saying that the physics doesn't care about the exact positions of the particles, just their arrangement relative to each other. Like, if we slide those lines around without changing their order along the root line, the scattering outcomes are identical.
Precisely. And that assumption, it really simplifies things. It means we can reduce this whole problem of defining our scattering theory on rank 3 PRLAs to just a single combinatorial type.
I see. So instead of worrying about all the different ways those three lines can intersect, we could just focus on one case, because z-symmetry tells us the others will behave the same way.
Exactly. It's a powerful tool.
Okay, so focusing on z-symmetric scattering theories makes things a lot easier. But what about that Yang-Baxter property you mentioned? How does that fit into all of this?
Well, the Yang-Baxter property is a key consequence of that focus on z-symmetry. Basically, it tells us that our scattering theory, it's invariant under those z transformations we've been talking about.
So no matter how we shift those lines, as long as we keep their relative order along the root line the same, the scattering data assigned by our theory stays the same.
Exactly right. And this has a really deep meaning physically. It means that in systems that have that Yang-Baxter property, those multi-particle collisions, they can be reduced to just a series of two-body interactions.
Wow, so we can break down these potentially really complicated events into simpler pieces. It's like solving a puzzle. Figure out how the individual pieces fit first.
Great analogy. And that factorization property, it's one of the hallmarks of those integrable systems, which is what the paper is all about.
Okay, I'm starting to see the big picture now. Scattering theories, they're operad morphisms that map PRLAs to scattering data. And the Yang-Baxter property, it makes sure that mapping is consistent with that z-symmetry.
Exactly.
But how do we actually construct these scattering theories? Where do we even begin?
Another good question. And this leads us to some pretty fascinating math. One way to build them is by using these objects called R matrices. Essentially, they encode the rules for how two particles scatter.
So R matrices are like the building blocks of our scattering theories. They tell us how the simplest interactions work, and then we use those rules to build up to more complex stuff.
Right. And these R matrices, they have to satisfy certain conditions to make sure the scattering theory they define as well-behaved. Those conditions, they come from the Yang-Baxter property.
Like a quality control check, making sure everything's playing by the rules.
Exactly. It's a really intricate interplay between the algebra, the geometry, and the physics.
All right, we've covered a lot here. Scattering theories, Yang-Baxter property, R matrices. It's clear this framework gives us a really powerful way to describe scattering physics. But there's got to be more to the story, right?
Oh, absolutely. There's always more to uncover. In the last part, we're going to connect all this to some pretty cool geometric constructions and talk about some open questions that are really pushing the boundaries of this whole area of research.
Okay, I'm on the edge of my seat. All right, welcome back, everyone. We're wrapping up our deep dive into scattering diagrams and operads, but we still have some pretty intriguing stuff to cover.
Definitely. We've gone pretty deep on the algebraic side of things, but there's this whole geometric dimension that's just as fascinating.
Okay, I'm all ears. What kind of geometric objects are we talking about here? The paper mentioned something called a permutahedron.
Yeah, the permutahedron.
I gotta be honest, that name sounds a little intimidating.
It's not as scary as it sounds. Think of it this way. A permutahedron is an object, a shape, really, that captures all the possible ways to order a set of things. Like, imagine you have 3 particles.
Okay.
There are 6 different ways to order them on a line, right?
3 factorial.
Yeah.
3 times 2 times 1, which is 6. So each ordering is like a different arrangement of those particles.
Exactly. And the permutahedron for 3 objects, it's a hexagon. Each vertex of that hexagon, it represents one of those 6 possible orderings. And the edges, they connect vertices that differ by just swapping 2 objects.
Okay, I'm starting to picture this. So 3 objects, we get a hexagon. 4 objects, we'd get some higher dimensional shape and so on.
Right.
But how does this all connect back to our scattering diagrams?
Well, remember in the transmission picture, that scattering process, it's all about particles changing their order as they interact. We can actually think of that as a path on the permutahedron. Each point along that path, it represents a specific ordering of the particles.
Ah, I see. So as particles collide and swap places, we're basically tracing a path on this permutahedron, hopping from one vertex to another along the edges.
Exactly. And this geometric picture, it gives us a way to actually visualize the scattering process in a totally different way. For example, if our PRLA is in general position, meaning the particles only collide two at a time, the path on the permutahedron, it'll only go along edges and vertices, no cutting corners through the middle of the shape.
So we're taking a very specific route on this permutahedron, following the rules, so to speak.
Right, and different combinatorial types of PRLAs, they'll correspond to different paths on the permutahedron. Those three rank 3 arrangements we talked about in the paper, they actually give us 3 different paths on the hexagon.
It's really cool how these kind of abstract algebraic concepts, PRLAs, Operads, they have such concrete geometric interpretations.
And it doesn't stop there. Even those phase shifts we talked about, they have a geometric meaning too.
Oh, really? How so?
Okay, so picture 2 particles about to collide. In our diagram, that's 2 lines about to intersect, right?
Yeah.
Now, instead of letting them actually cross, we slightly shift one of the lines parallel to itself so they just barely miss each other.
Like those particles swerved at the last second to avoid a head-on collision.
Perfect analogy. That little shift, that's a phase shift. It's a measure of how much the particles' positions have changed because of their interaction.
So we can literally see those phase shifts as displacements on our diagram. Like geometry is giving us this zoomed-in view of those interactions.
Exactly. And this perspective can be super helpful for both understanding and calculating those phase shifts, which are, key to describing the whole scattering process.
It's amazing how these different areas of math, the algebra, geometry, combinatorics, they all come together to give us a deeper understanding of these physics problems.
And the really exciting part is we've only scratched the surface here. There are still so many open questions, so many directions for future research.
You can't just leave us hanging like that. Give us a glimpse of some of those mysteries waiting to be solved.
Okay, well, one really interesting avenue is to look at scattering theories that take values and categories with even more structure. Categories that, capture information about homotopy.
Okay.
This could help us understand the topology of particle interactions in a much deeper way. Maybe even connect quantum field theory and topology in some new way.
It's like adding another layer of depth to our understanding of how particles interact.
Exactly. And then you've got these big challenging questions like figuring out the role of operads and scattering diagrams in a deeper theory of quantum gravity.
Wow.
Some physicists think they could be the key to unifying quantum mechanics and general relativity.
That's a pretty ambitious goal.
It is, and that's what makes this whole area so exciting. It's this beautiful mix of math, physics, and these really fundamental questions about, the nature of reality.
I think it's safe to say this deep dive has really opened my eyes to a whole new world.
I'm glad to hear it.
We started with these simple particle interactions on a line, and now we're talking about these really complex mathematical structures that could revolutionize our understanding of the universe.
Well said. It's a fascinating field, and I hope our listeners feel the same way. There's so much to discover here.
I think they do. Thanks, everyone, for joining us on this deep dive, and we'll be back with more soon, so stay tuned.